Now, hello and welcome to HPG 2022, the High Performance Graphics Conference. I am your session, I'm not session chair, also the general chair for the conference. My name is Jen Yüksel. It's right here somewhere. So this year, HPG is going to be virtual, and also we're going to have an in-person event co-located with SIGGRAPH. I'm going to get to that in just a little bit. Now, for those of you who are joining us for the first time, let me give you a very brief introduction to HPG. The High Performance Conference, High Performance Graphics Conference has been around for some time. It's about performance-oriented graphic systems, and we have a whole bunch of topics that we explore in this conference, like algorithms and efficient implementation languages, compilers, parallelism, hardware. It's everything and everything in between. And in this conference, you will see a good mixture of researchers both in the industry and academia. And HPG has been around for quite some time now. This is actually the 14th year of HPG, but the roots of HPG can be traced back in time quite a bit. It actually started with the Graphics Hardware Conference in 1986, and that was Eurographics graphics hardware, and then turned into SIGGRAPH, Eurographics graphics hardware. And right around 2000, 2008, 2009, we also had programmable GPUs coming up. And so interactive ray tracing became something really popular, and we had the Interactive Ray Tracing Conference. And then the contents of these conferences actually were very closely related, so it was a very, very natural thing to bring those conferences together, and that brought us to HPG that we know and love. Now, HPG started in 2009, and we've been in person all this time, except for the last 3 years you see here. We have been virtual. And when of course, in 2020, most conferences became virtual, and HPG was no exception. Actually, we decided to be virtual pretty quickly in 2020. And after that, we kind of liked this format, and we wanted to continue with it. So we'll see how things will go in moving forward. But we are actually very, very happy with this format, and I hope that you guys are enjoying it as well. Now, this year, HPG is going to be virtual, as I said, but it's virtual with an asterisk. I'll get to that asterisk in just a little bit because, the in-person event. Now, there are two ways to enjoy our virtual conference. One is our free online stream. It's completely free. You don't need to have any registration or anything. You just go on YouTube or Twitch, and you can see our content. You can watch this freely. You don't have to do anything. But we also offer a premium registration. This will allow you to interact with the speakers, interact with the other attendees in the conference, and this is going to give you a real conference feel. And for that, we made the fee as nominal as possible. It's just $15, and you register for it, and you'll have the link to our OEA platform, and you'll be able to interact with us. And the conference is going to be, the virtual part of the conference is going to be 4 days. It's about 3+ hours. I'm saying 3+ because we have 3 hours of streamed content, and then we have some other activities after that. That's for most days it's going to be on OEA, but one of the days is going to be streamed after 3 hours as well. And of course, we also have an in-person component, and that's going to be an in-person reception and keynote, which is going to be much later in August 7th, co-located with SIGGRAPH. I'll get to that again. I'll remind you that one again. But I want to talk about our OEA platform just a little bit. It's about of course, you need to have premium registration to get into OEA. What it provides is obviously video chat, so you can chat with people directly, and that's going to be happening in our interactive rooms, in social events. You will be able to see people like this, and you can talk to them. They'll be able to hear you and all that. And we also have a possibility of side conversation. So if you want to talk to someone directly, you can actually click on this icon on top right here, and then you'll be able to call them aside and talk to them directly, and other people won't be listening to you. There's also step up to the mic option. So when we have a Q&A session in this auditorium, you will see that at the bottom here, there's going to be an icon, and it will show step up to the mic, and you click on that, and you will be on stage. You'll be also on broadcast, and your camera will be visible to everybody, and you'll be able to talk to the presenter and the session chair. We also have text chat, which is kind of important. You kind of need to turn it on to be able to see it. And that's going to be at the top left corner, right up there. There's an icon in OEA, of course, not in the stream, in OEA. If you click on that icon, you will see that the chats will pop up on the side. And with that chat, now I need to remind you, just say one thing about that chat. That chat is specific to you. So that's the room chat. You'll see everything that's in the room while you're in the room. If you step out and come back, you won't see prior messages. So this is all live, and you only see the things that you have witnessed, all the messages that were sent while you were there. And if you leave the room, those messages will not be cleared. You'll see the history of everything that you had seen in the past. All right. So chat is great. I'd recommend that you turn it on and start using it. But there's more, actually. Now, we have a whole bunch of rooms in OEA. This auditorium is this one. The auditorium is the one that is going to be in the broadcast. And this is our special room. And you'll have reactions down here. You actually have more reactions, so you've seen some icons popping up. So you can use them freely at any time without being too disruptive, I guess. We also have a poster hall, which is where our posters are presented. We have our student competition and a town hall and social rooms. Now, social rooms, I want to talk about them just briefly. Now, I know that you guys have probably been to some online social events. This is going to be quite different. I'm telling you, this is going to be different, and do not miss that. And this is going to, we worked a lot on this, actually. We spent a lot of time on this. Our online chair, Nick, specifically, spent a lot of time on designing these rooms for us. So I would highly recommend it. For example, you can just go into Crytek Sponza. Wouldn't that be cool? And have some chat there. Well, if you're maybe want to grab a bite to eat, we have San Miguel. If you prefer a closed space, of course, we have the breakfast room. Or for more serious conversations, we have the conference room. If you want to have a cozy place, we have the fireplace. And if you want to actually have some challenge, we have puzzles. We actually have 2 puzzles that you can play cooperatively and see if you can get them done. Now, as for the conference content, we have Keynote, we have invited talks and technical papers, of course, and posters and panels and student competition. I will not tell you the entire program. Instead, I will ask you to go to our website and check the program online, because the program here online will actually show the program on your time zone, which is probably more important than me telling you when things are starting in my time zone. All right, but I would like to go over this content really briefly. We have some amazing keynotes lined up for you here at day one. We're going to start this keynote in just a few minutes. And then we have day two keynote. Day three, we don't have a keynote. I'll tell you why. But we have keynote in day 4, and we have a keynote at the in-person event. In day 3, we don't have a keynote because we have Hot 3D invited talks instead. Day 3 will start with Hot 3D invited talks. So I would highly recommend that you do not miss that. This hasn't been happening, actually, a Hot 3D event for some time. We're very excited to bring it back to HPG. We also have other invited talks as a part of our diversity and inclusion program. Now, most of these talks will be directly about the diversity issues in our community and in computer science more broadly. And those are very, very important topics that I would really like all of you to pay more attention. Do not miss these talks. So one of them is going to be a little bit different. This is going to be a talk giving some sound advice for grad students and for early career scientists. I would highly recommend that you see all of these talks. Actually, for that, we put them at prime time. So these talks are going to happen right before paper sessions. They're just 20 minutes right before paper sessions. Please make sure to see them. They're going to be amazing. Now, we also have a panel on high-performance geometry that's happening on day 3. This is going to happen after the paper session on day 3. So I'm super excited about this as well. I'm really looking forward to it. Now, with that, let's talk about our technical papers program. And for that, I would like to bring Joseph on stage. Yeah. Hi, Joseph.
Hey, Jem. Thanks for the introduction. So we have 12 excellent papers that we accepted at HPG this year. We followed a pretty standard double-blind review process with online reviewer discussion, and we actually had a pretty shortened review timeline, getting conditional decisions to authors in only 18 days. We did have a 2-stage review as required by the proceedings of the ACM for computer graphics and interactive techniques. That's the journal that all of HPG papers are published in this year. And I think the process went pretty well overall and improved the quality of the accepted papers through the process. We'd like to thank the International Paper Committee. Each of these individuals helped greatly with their reviews. They provided excellent reviews, and I believe all of the submissions will be improved in whatever their final form is because of the high quality reviews. As I mentioned before, all of these papers are going to be appearing in a special issue of the Proceedings of the ACM on Computer Graphics and Interactive Techniques. They will be all open access and available on the ACM Digital Library. The links are not yet live on the website, but they should be soon, so you can check out all of the papers there. And I believe we'll talk about posters next. So let's have the poster chair, Jonathan, speak next. Thank you.
It should be my turn now.
Hey, Jonathan, we're waiting for you. Go ahead.
Where should I click?
You don't need to. You're here. You can just talk.
Oh, you can hear me? Okay,
Absolutely.
Sorry. Okay, hello, everyone. So sorry, I'm this year's poster chair, and I'm happy to announce that this year we have 7 posters, and they have a very diverse set of topics. So we'll have real-time caustics, multi-view rendering, a tessellation shader, denoising, real-time GI, a compression scheme for opacity texture maps, and some learning for PRT. These posters will be available throughout the entire conference, and you can check them out during the entire conference in the OEA chat room. But the poster session where you get the chance to interact with the actual authors will be in 3 hours. And before that, you'll get a quick fast-forward video where you get to see for a brief minute an overview of the entire contribution. So see you later.
Hi, I'm Christoph Schied, and I'm the chair for the student competition together with Angel Patney. And in this year's student competition, the task was to optimize the real-time path tracer that was hosted on ShaderToy. And so the participants had a given performance budget, and the goal was to achieve the highest quality possible in the budget. We received 9 submissions in total from all over the world. And we saw a variety of different optimization strategies. So, for example, denoising, improved sampling techniques, or pre-computation. You can see these submissions in the specific OEA room. They also have a brief description with them that describe the optimizations that were performed. On Thursday this week, we will announce the winners of this competition, and the winners will receive Intel Alchemist GPUs. So yeah, please check it all out.
Oh, talking about awards, we also have other awards at HPG. We have the Test of Time Award that's going to be for papers that were published and presented at 2012, HPG 2012. And we have Best Paper Award, Wolfgang Strasser Best Paper Award, and the Best Poster Award. So these 2 awards are actually selected by you, by whoever is in with premium registration, whoever's in OEA. You will be able to see a link up here somewhere where you can click and see all the papers, and you will see something similar when you go to the poster hall, and you can vote and pick the best poster and best paper for our conference. And this year we're going to have something special again by Intel. The selected awards will also get this Intel Alchemist GPUs. Now let's talk about sponsors. Our sponsors play a critical role in making this conference possible, and would like to give a special thanks to Intel, Reality Labs, and Unity. As nurturers, they played an especially important role in our financial success. And we are also grateful for our benefactors, Activision, Adobe, AMD, and NVIDIA, for their reliable support. We also thank Finally, ACM and Eurographics serve as a legal and financial services sponsor, enabling us to sign contracts and publish the proceedings. As I mentioned, we have an in-person event following this virtual conference in August 7th. The Sunday before SIGGRAPH begins. It's co-located with SIGGRAPH. It's going to be at the Harbor Center. Do not miss it. We're going to provide a buffet-style dinner, but that requires full registration. So you just a little bit extra, and the total comes down to $40 and $40, and you will be able to join us. And actually, do register this week, because this price is going to have to go up a little bit after this virtual conference ends. So please make sure to reserve your seat at the in-person event. And we will have, of course, a keynote that I mentioned by Brian Harris, Journey to Nanite. Do not miss that. Well, this is not going to be streamed live. This is not going to be a hybrid event. It's going to be a real in-person event. So we'll be able to interact with each other in person, also enjoy this wonderful keynote in person as well. Now, if you like this whole program, there are a whole bunch of people to thank, and I don't want to just thank them by their names here, I actually want to know, this is an interactive platform, right? So I want to bring them on stage and thank them here. So let's start with our paper chairs, Joseph and Mark. Hello. If you like the papers, you should be thanking Joseph and Mark. All right. Next up, our program chairs, Angel and Tammy. They have been putting together this amazing program with these keynotes for us. Thank you so much, guys. And our poster chair, Jonathan, that you saw a minute ago, and Constantine, our registrar this year. Our treasurers, Steve and Dave. Actually, Steve also, they are making sure that we're not going broke. But Steve also played a critical role in putting together our in-person events. So thank you extra, Steve. Our student competition chairs, Christoph and Angel. Okay. Check them out, and oh yeah, we had some amazing submissions this year. Our diversity chairs, Noshaba and Esteban. They helped us bring some amazing invited talks as a part of our diversity and inclusion program. And also our publicity chairs, Noshaba and Andrew this time. I would like to thank Andrew again, actually, because he's been great at putting up with my constant request for updating the website, on top of updating our entire web infrastructure. He's been doing that, and he did one more thing that you guys will love. I think it's coming up in a second. We have a little surprise for those of you who register for HPG. I'll tell you in a little bit. But before that, let's thank our online chair, Nick, who graciously put together this OA space for us. If you enjoy what you see here, Nick is the person to thank. All right. We also have other people to thank, of course. Andrew, you're still here. Well, we'll talk about your stuff. Don't worry. Also, Kayvon was super helpful in putting together this really complicated auditorium for us. Thank you, Kayvon. And Pierre is helping us actually manage it, run the show. And Thomas and Christoph were very helpful in the student competition. Ashley is always helpful for the ACM stuff for us. And Jacob has been helping me for organizing the conference. As I said, we have a little surprise, a little conference gift while supplies last. So this is something that Andrew designed, an actual physical Cornell box. Now you can flip it over and, of course, put your pen and pencils if you want to. Or there's a light hole back there. Actually, you can put a light, and let's see what kind of photos you can get with this, and see if that will match your renders. We'll find out next year, I guess. And there's going to be a short session where Andrew will be telling us how to put it together. So he not only designed this, but he's also helped us. Well, he helped manufacturing with the manufacturer, and he's painting all these Cornell boxes himself by hand. So thank you again, Andrew. All right, I think this is enough time for the introduction. Let's switch to our keynote session. I'm really looking forward to this. Now, today's keynote is going to be by Petrik Clarberg. He's a principal research scientist at NVIDIA Research, where he joined the real-time rendering research team in 2016. Most recently, he has focused on systems and algorithmic research for real-time path tracing. Prior to NVIDIA, he was a real-time rendering researcher in the industry for many years and co-founded a startup. Petrik's passion for graphics started with the 1990s demo scene. He received his PhD in computer science and engineering from Lund University in Sweden. So let's hear from Petrik.
Hello everyone, I'm very happy to be here today, virtually at least. My name is Petrik Clarberg, I'm from the real-time rendering research team at NVIDIA. So, over the last few years, we've explored real-time path tracing. The goal has been to build a full real-time path tracing pipeline, push it to its limits to see where it breaks. So I'll talk about the findings from this work today. A large number of people have helped with this effort. So I especially want to call out my closest collaborators who are mentioned on the slide here. So I'll divide this into two parts. Part one, I'll show a bunch of visual results, talk a little bit about the technical side of the path tracer. For the ones who saw my GDC talk earlier this year, there'll be some amount of overlap, so please bear with me. But I've also added quite a lot of new content. Then for the second part, I will focus on open problems, the type of things we're currently thinking about. What are the next steps for real-time path tracing? So stay tuned for that. Ladies and gentlemen, this is real-time path tracing today. This is rendered on a single RTX 3090 GPU, 1080p resolution, as are all the results I'll be showing today. So here we're following paths of up to 30 bounces in length without any hacks or approximations. The path tracer itself is an unbiased path tracer, and then we take the output and denoise that to produce the image. I like this tiger shot, even though we've shown it before, both because it looks very real, and second because the stats for the scene are just impressive. So the tiger is a skinned character. It has a mesh with the bones and animations inside, and then there's a fur that is explicitly modeled with hair strands. In total of 3.5 million hair segments. It's walking through this very dense jungle, which consists of 3 billion instanced triangles. And especially here, note the FPS counter in the top left corner. So it's running this particular shot 33 FPS. It's stable at above 30 FPS throughout the animation. So what led us to this point? It's really the dream, which I think I share with many of you in the audience, is the dream of being able to take any 3D content and render it photorealistically in real time. And we define real time here as 30 milliseconds or less per frame. So how does one render something photorealistically? I'll keep it short. So the mathematics are described by the rendering equation, which was introduced almost 40 years ago, and even before that in other fields like physics. So path tracing solves the rendering equation by stochastically sampling the incident lighting. That is done by tracing paths that bounce around in the scene until they randomly hit the light source. In order to increase the chance of actually hitting a light source, a technique called next event estimation is often applied, where we at each bounce explicitly sample the lights by randomly picking a light and then tracing a shadow ray towards it to evaluate the visibility of it. So path tracing is an elegant solution to the render equation because it takes all types of light transport into account in the same framework. And it has completely taken over visual effects and film rendering over the last 10-15 years. However, it is computationally intensive because you have to, first of all, you have to trace a lot of rays. At each point along the rays, along the path, you have to do the shading, you have to do light sampling, many other operations. And then second problem is that since these paths are random, there's a lot of shader divergence and very random access to the memory. So in addition to that, why is real-time path tracing particularly hard compared to offline rendering? So there's several reasons for that. One is just the sheer difference in the computational time that is available. So for film rendering, it's common to have a rendering time of 24 compute hours or more per frame, whereas in real time, we have to stay under this 30 millisecond limit. And out of those 30 milliseconds, some of that is other things like denoising and everything else that the application has to do. Another more subtle difference is that in a film or a visual effects rendering, the shots and the lighting are carefully directed. Whereas in real time, many times as the camera is a free camera controlled by the user, you can walk around anywhere in the scene and the light transfer just needs to work wherever you look. And then third, for professional film rendering, the content and the artist is often trained what to do and what not to do to avoid breaking the render. Whereas in real-time graphics, many times the content might have some issues. It might even be user-created content. The contents may be made for a rasterization engine that has very different requirements than a path tracer. So for all of these reasons, we say that real-time path tracing is at least a 3 million times as hard problem as offline rendering. So let's look at some results now. So to make real-time path tracing more useful for graphics research, we've recently added a PBRT scene importer that loads the scenes that are used for Matt Farr's book, Physical-Based Rendering. Those scenes are typically used for offline rendering research, but as we'll see, these are now available for real-time path tracing use for real-time graphics research. So in the background here, I'm showing the landscape scene, which is the identical scene as was used on the book cover for the 3rd edition of the book. You can see that the render is at 38 frames per second. This is with 10 bounces of path tracing. And the stats here are 4.3 billion instance triangles. Another metric that I want to point out is that the scene has over 400,000 instances. So I will now, here you can see the scene without the book covering it, and I will now show some more screenshots of it. So here is looking over the fence. This is at 35 FPS. And then there's a pond in part of the scene, so this is showing the reflections in the water surface there. You can see the very dense foliage that is reflected off the water here. And then for this view, this is at 43 FPS. So all of these are directly just screenshots from the real-time path tracer. So again, I want to point out that this is no longer a scene only exclusively for offline rendering use. You can now actually path trace this in real time for your research. So path tracing is often associated with rendering glass and transparent materials. It's hard to fake those kind of materials without actually following the full light paths correctly. So to show an example of this, I've here loaded the transparent machines scene. This is actually made by the same artist at the 0 day scene that I'll show in a moment. This gives a good idea of what's possible in real time today for glass and other transparent objects. So you can see we're tracing this with 30 bounces of path tracing. The object itself has 3.6 million triangles and about 851 mesh instances. So as you can see, there are still some black spots in it. Those are indications that some paths still at these number of bounces get stuck with total internal reflection, and that you would need even more bounces to remove those. We've tried with 100 bounces, then it runs slightly lower than 30 FPS, but still fairly useful. So one of the things I mentioned in my GDC talk was adding support for more complex materials to the research path tracer. We've now done that over the last couple of months. We've added support for all the real PBRT materials, including coded diffuse, coded conductors, and also support for the measured MERL and the anisotropic RGL materials from the EPFL database. So this scene, the sports car, uses almost entirely these measured anisotropic RGL materials. So it's an example of showing rendering with these other material shaders. Here we're also using the same settings here. These are the defaults for the path trace of 10 bounces, has 7.2 million instanced triangles. So this is an outdoor scene, of course, so it's a fairly simple light transport, but there are some effects like the real lights you saw, the windscreen, and some other parts where actually many bounces are required. So here is another very common scene from rendering research. This is the PBRT country kitchen scene that we path trace also in real time. This has been used in numerous rendering papers. You probably recognize it. This runs at stable 60 frames per second. And then similarly, the PBRT bathroom scene. This also again renders at about 60 FPS. The main challenge in this scene has been the denoising of the glass light bulbs that you see hanging above the mirror. So keep an eye on those when I play the clip. And that case is particularly challenging because it's denoising something that's only seen through reflection. So as you noticed, all of these PBRT scenes are static, but we also wanted to show an example of dynamic scenes because the path trace has no pre-computation, so you can really handle anything that is dynamic and both moving light sources and moving geometry. So for that purpose, we have this 0-day scene done by digital artist Mike Winkelmann. We've shown this several times in different demos over the last years, and the reason is that it's a really good stress test for the denoiser, and every time we show it, we have some improvements. So as you can see when I play it, it features very glossy materials, makes it hard to denoise. It's also very quickly moving lights and moving geometry. Performance here is around 60 FPS, 3 bounces, and 6 million instance triangles, and then the lighting comes from 10,000 emissive triangles. And when we saw this when we saw that we were able to render this in real time, we really thought that we need to push this much higher and see what the limits are. So therefore, we got this beautiful scene of Turbo Squid, which is really made for offline rendering. It's incredibly detailed when you zoom in. Look at the details, like the chandelier and the chairs and all parts of it. Here there are 25 times as much geometry as in 0-day and 50 times as many lights. So the lighting comes from 500,000 emissive triangles, and then on top of that we have added 30 dynamic spotlights to make it even more interesting and also dynamically changing. So both 0-day and this scene are indoor scenes with we used 3 bounces of path tracing for them. Performance for this scene is about 30 frames per second. 0-day was 60 frames per second. So that shows how well path tracing scales logarithmically with increasing complexity. There's more than an order of magnitude more geometry and more lights, but only half the performance. So finally, I also must show the tiger in action. This is a live capture from a path tracer. It runs stable at 30 frames per second. As you can see, the tiger's walking here along the waterfront. The jungle is not seen much in this shot, but it's actually 3 billion instance triangles. The main complexity is the light transport in the fur for these images. And the lighting comes from an environment map and then a separate distant sunlight. That light is filtered through the canopy, and the leaves have a diffused transmissive material. So this kind of illumination is just very difficult to approximate without path tracing. Here is to give you a sense of the scale of the jungle. I've circled the location of the tiger with the red mark. So when I play now, you can look closely there. You can see that it's walking on this little island, and the camera will be moving around to show you a bit of the scale and what it looks like more up close for the trees. And then finally, we also wanted to test animated foliage. That's a particularly tricky case because it requires updating the BVH, the acceleration structure, every frame for a large number of triangles. So to do that, we've added a wind animation. So the leaves here are swaying in the wind a little bit. And also note that we don't use any alpha testing and no LOD for this scene. So it's really just path tracing against the geometry at the finest scale. So every single leaf is modeled with triangles here. And in a real application, I should say, you probably want to use both LOD and alpha testing to reduce the complexity. But nevertheless, performance is very good actually. It's between 45 and 50, 60 FPS. As you can see when we drag the slider here, the time of day changes. So both the environment map and the lighting changes, and the leaf animation changes. So let's talk about what are the most important performance optimizations we've done. A lot of this effort has been about understanding path tracing performance on the GPU and avoiding bottlenecks. So maybe the most important is optimizing for cache efficiency. So the GPU has this memory hierarchy with a large chunk of DRAM and then smaller caches. We really need to make the best use of these caches. And since path tracing is essentially a random access algorithm, it's really important to both compact your data as much as possible so that you can fit more in each cache line. Think about cache line alignment of your data structs, minimize the number of indirections when you do access memory. Really everything you can do to minimize the number of cache lines that are touched when you do access memory from within the path tracer. Then another important aspect is material complexity and number of shaders executed. I mentioned earlier that one of the problems is shader divergence. If you have thousands of shaders, then it's very difficult to schedule that in a good way. So what we do is we kind of take a drastic approach for the research path tracer to bake down the original MDL material shaders into a smaller set of PBR material models. And then we're taking a bottom-up approach to gradually add back more material shaders. So for example, we've added now back all the PBRT materials, we added measure materials, but we do this carefully to see how much complexity we can bring back while still maintaining the real-time rate. Third, we've done a lot of scheduling experiments over the years. I can't go too much into detail on that, but one of the main conclusions has been that when you have any kind of wavefront architecture where you trace one bounce of path tracing, write out all the hit points to memory, and then maybe sort and then trace the next bounce, any kind of wavefront architecture like that is always going to be bottlenecked on the memory I/O. So that's why we say that it's really important to keep your work on chip as much as possible. And the recommendation is actually to leave the scheduling choices to the driver, because the driver has more low-level knowledge. It can decide when to run which shader to be able to keep the data on chip better. And then fourth, important aspect is also optimizing your assets, and in particular your BVH acceleration structures for ray tracing and path tracing performance. So the main challenge here is mapping the often deep scene hierarchy onto the one-level instancing hierarchy that the ray tracing APIs provide. And what to optimize for there is to minimize the spatial overlap between the bottom-level acceleration structures, just to increase traversal performance. So now we've taken all these optimizations and implemented them in a full real-time path tracing pipeline. This pipeline consists of three main parts. There's a front end and then a light transport phase where the majority of frame time is consumed, and then a post-processing pipeline which denoises and produces the final image. For the front end, this is fairly similar to what current raster engines do, at least the engines that support ray tracing. So it's handling all the scene updates, it's updating the BVH acceleration structures if they're animated or skinned content. And then we also include a VBuffer pass here to compute what is visible from each pixel. And the reason to do that is that this information is needed both by the path tracer to launch the paths from, and also by the post-processing pipeline for the denoising and post passes. So it makes sense to amortize that cost. Second, As I mentioned, the light transport phase is the most complex. Here we use the GeForce SDK called RTX DI, which is based on Reester. It's a productization Reester. We use that for the direct lighting. It handles diffuse and glossy reflections. And then the path tracer simulates all other types of light transport. We usually run that at between 3 and 30 bounces. So that includes ideal specular reflections, a transmission, all types of transmission, all the indirect lighting, and so on. The path tracer also outputs guide buffers, which the denoiser then consumes to be able to produce the image. And we also in the code have an option to enable a probe-based irradiance cache that is provided by the RTX GI SDK. We do not use that for any of the results that we show today, but it's an option to enable that to get even better performance by then reducing the path length and instead terminating them into this irradiance cache. So, and then finally, there's the post-processing pipeline, which is really critical for producing the image. We built this on top of the NVIDIA's real-time denoiser library NRD. So NRD provides a set of spatiotemporal denoising kernels. We've combined those in a way. I'll show an example of that a bit later. We also run DLSS, the deep learning supersampling. We run that at 100% and no super res, just to provide anti-aliasing a little bit, remove some residual noise that is left by the denoiser. And then there's some post passes, very traditional tone mapping and maybe depth of field and bloom and so on, if those are desired. So this completes the pipeline. You can, we have source code for this that is open source. You can go look at all the parts of this and how it works. So finally, I'm sure you wonder now, how is the time spent between these three phases, between the front end, the light transport phase, and the post-processing. So I've measured that on 3 different scenes. First, the tiger scene, which is the most complex of the ones we showed today. In that case, the path tracing itself is about 50 or so % of the frame time. The rest is the front-end work, where there's quite a bit of animation and updating of the BVHs, and then the denoising and post pipeline there that takes the rest. Landscape scene behaves similarly. It's a similar complexity in the number of triangles and actually the look of the scene itself. So the light transport there is on par with the tiger scene, even slightly more. But the front-end work is less because it's not animated. And then there's the transparent machines with 30 bounces of path tracing, where the light transport phase is about 13 milliseconds. And then finally the car scene, where the majority of cost is actually evaluated in these measured RGL materials. The code for those are fairly complicated. So I want to say a few words about the implementation of the path tracer. So the implementation was a challenge on its own. And one fundamental observation is that path tracing is a unified rendering algorithm, and therefore all the rendering code that is needed for the frame needs to be available at the same time. When you trace array, you can hit anything in the scene. You need to be able to shade at that point, you need to be able to do light sampling, update the dielectric stack, do all the logic for the path tracer, and so on. So you really need all the shader code in one place. And we've implemented this as a single DirectX ray tracing program. This program have then different entry points for the ray generation shader, for the different hit shaders, any hit shaders if there's alpha testing, and the large amount of shared shader code for all the BSDFs, the materials, light samplers, everything else that's needed during the frame. And as I said, the complexity of this gets very large because it's everything that is needed for the full frame. So even for the research path tracer, this is already up to tens of thousands of lines of code, shader code. And we quickly realized that current shading languages like GLSL and HLSL, they're not at all built for this kind of complexity. So the question is really, how do you write modular and extensible shader code support, all these different sampling strategies, all the different materials, depending on what the scene needs, and able to dynamically add or remove those without creating a mess, unmaintainable mess of the shader code. So to address this, we build on the Slang shading language. So Slang is foundational technology for NVIDIA Omniverse and also for all of our graphics research. The goal of Slang is to support exactly this use case, being able to write large production shader code bases in a modular and extensible way. And the strategy often taken is to adopt carefully proven mechanisms from other languages like Rust and Swift, and then implement them in Slang in a GPU-centric way, so that performance still is as good as it can be. And many of these features have actually been co-developed with the path tracing research. So we developed the language jointly with the path tracer. Slang is open source, and it also compiles to a large number of APIs, including Vulkan, DX11, DX12, CUDA. So, and the important thing is that it's backwards compatible with HLSL almost entirely. So if you have existing shader code, it's really easy to switch to Slang and then benefit from all these modularity features it provides. So I won't have time to go into too much of what it can do, but I'll show one example of something that is very useful. So Slang has this concept of interfaces. An interface is kind of like a base class in C++ that tells you which operations a type can implement, but not the actual implementation of those. And then you write your implementation, in this case, a random number generator, that then implements these interface operations. And the power of this is that now you can have many different implementations of the same interface, and you can write generic functions that then operate on the interface type without knowing exactly what type you pass into it. So that the types then can be either statically created or even dynamically created in Slang, but your rendering code can be written generically to handle any kind of thing. So this is super useful. We use this for essentially everything in the path trace. Use it for all the BSDFs, all the materials, the light samplers, and everything else. So here I wanted to show you some pointers to source code. So as I mentioned, the Falcor real-time path tracing research renderer is fully open source. It shows you how to integrate all of these NVIDIA SDKs that I've mentioned: RTX DI, RTX GI, DLSS, NRD for denoising, and MDL for the material description language. It shows you how to integrate this in a real-time path tracer. And since we are limited on time today, I'm going to leave it there. But you can go see my GDC talk for more details on the technical side of the implementation of this path tracer. So the link here points you to that talk. Similarly for the Slang shader compiler, of course, you're free to use that independently of the path tracer. But Falcor is using it throughout, so all the shaders you'll see are written in Slang, and same here, we have a longer technical talk that you can go watch if you want more details on what Slang can provide and how it's built and what APIs it can target. So that concludes the first part of this talk. Now we can stretch our legs a bit for 1 second and think about what we've just seen. Real-time path tracing are really quite large and complex scenes, including the well-known PBRT scenes, which are now available for real-time graphics research using path tracing. I would say that these results have fundamentally changed the way we think about real-time graphics research. There are no more shadow maps, no ambient occlusion passes. It's really unified onto improving the light transport, improving the denoising, improving the content. So, end of break. For the second half, I want to focus on what is next, the top 3 areas to improve on. and with this dream in mind of being able to photorealistic render any type of 3D content. So, as I mentioned earlier, real-time path tracing often do not have as much control over the content as an offline production. So an important open problem is more robust and better sampling methods that can handle even in some cases poor content. So here's a simple example I'll be used to illustrate one of the many common problems we see. Both images here are path traced with identical settings. It runs at about 150 frames per second because it's a very simple scene. But the right one doesn't look quite right. If you look closely in the corners, for example, there's blotchiness, it has weaker color bleeding, and generally it's a bit darker than the one on the left. But it's supposed to be an unbiased rendering, so what is really going on? And this is a common question that is not always easy to answer. So when loading arbitrary content into the path tracer, sometimes it works very well, sometimes it doesn't, and it's important to be able to find out why. In this case, where if I turn off the denoiser, you can see that the samples on the right are almost entirely all black. So the denoiser has very little data to work with and hence produces these bad results. But why is the sampling so bad? This requires some detective work to figure out. In this case, I know because I created it myself, but the reason is that we placed some bright lights outside the scene. They're always occluded, but they fool in the light sampling. And you would actually be surprised to find out how common this is in real scenes. There are many cases where there's super bright lights and they're just always occluded for no particular reason. Is this a content problem or a sampling problem? Well, I guess that depends on who you ask. Do you ask the artists? Then it's maybe more of a rendering problem. If you ask the rendering engineers, then they'll probably say, can you please go fix the content? But independent of that, we need to handle it. So I'm going to show some other examples. So that was a case of lights outside that are always occluded or almost always occluded. Another common problem is that there can be lights that are hidden inside of walls or partially inside of walls. Sometimes geometry is not properly closed, so some paths can escape into the interior of walls and so on. That can cause both issues with the volumetric stack and also performance issues. Sometimes emissive textures are very poorly used in that there can be a 4K emissive texture with only a few pixels actually lit up. Again, causing problems unless you're very careful to pre-integrate your emissive texture against the geometry, or otherwise handling where to sample on them. So in general, some of these issues are just caused by real-time content being authored for real-time engines, where these things maybe don't matter for the performance or the visual quality. Practically speaking, though, we realize that raster and path tracing will coexist for quite a while, so we cannot expect content to suddenly get a lot better. It's also very expensive to make fixes to the content. It requires talking to the artist, getting their time to actually fix these problems, that they have to understand what is causing it, and so on. So for that reason, I would say that more robust sampling methods that can handle even bad content are needed. And then second, I also think we need better tools to understand where and what is causing a particular rendering issue. So for association work, there are by now very well developed tools for analyzing performance problems or looking at where issues are coming from. We need similar suite of tools for real-time path tracing. So I will show an example how better sampling can help address this problem, even without changing the content. So here I've taken this bad version of the Cornell box with the extra lights. On the left we show the original path trace output. In the middle I show what happens if I enable RTX DI for the direct illumination sampling. So that takes care of sampling the direct illumination very well, even though many of the lights are occluded. And then on the right, we also enabled Restore GI, which is a solution for at least diffuse-ish indirect illumination using the Restore mechanism. So in that case, that is sufficient to handle this problem, that it's enough for these algorithms to find a few useful samples and then they're able to reuse those. So what about more difficult light paths? So this year, researchers in our group, in collaboration with University of Utah, have extended full path tracing, extended Restore to full path tracing. So in this case, we show the classical Vici-Guba scene, where lighting comes in through a small crack in this door, and then has to bounce several times through the scene in order before reaching the camera. So this is of course a notoriously difficult case to sample. It's often used for light transport papers to illustrate improvements in the sampling. So here I'm showing the path traced original output. This is with just traditional BSDF sampling, next event estimation, which in this case doesn't really help because the lights are not visible. Enabling Restore GI, which handles diffuse and glossy illumination on the secondary bounces. So note that the teapot in the front, which is very highly glossy, and also the teapot in the back, which is transparent, those are just not handled by this algorithm and turn out to be black because of lack of sampling. And then Restore PT, this year's extension, is actually able to find useful samples even on these type of materials. And here's the reference for solution for comparison. So the previous image was one sample per pixel, and this is using this is converged. So I'll show it in action. So as you can see, this is running at about 40 milliseconds per frame. Restore PT is not yet fully integrated into our real-time path tracer. The method is fairly involved and was developed in a separate framework, but that's one of the things we're working on to merge these two. So Restore is extremely successful at improving sampling quality. Once you've found an initial set of samples that are useful, then Restore can improve the quality of those samples. But you still need to find these initial samples, and sometimes that's very hard. Next event estimation is actually very fragile. Whenever your light source is inside glass, for example, or in water or outside water, you're in the water, whenever there's an interface between you and the light source, then traditional next event estimation just fails, and your shadow rays will always be occluded and just wasted effort. So one of the things to improve on is better next event estimation. One solution might be to implement specular next event estimation or specular manifold sampling and port those algorithms to real time. Could be very useful, I think, even though it's fairly complicated. Another open problem is sampling longer light paths through things like very long blonde hair, snow and ice, other media that requires many bounces, and then connecting to light source when you exit the media. So this photo actually combines it all. This is caustics lighting up long fur that is light color underwater here. So when we can render this in real time, we've made quite some progress. So as I mentioned, similar problem happens in snow and ice, and that's the reason we don't yet have any winter scenes in the real-time path trace results. It just doesn't work yet. So those were some challenging problems with sampling. Let's talk about denoising as well, because sampling and denoising are intrinsically tied together. Real-time path tracing would not be possible without both, and there's definitely room for improvement. So a path tracing denoiser uses the NRD kernels, and I'm going to keep this short, but what we're doing is essentially take the noisy path trace signal, decompose it into different frequencies, so diffuse reflection, specular reflection, transmission components, and so on, then denoise those separately, and then combine the result again to produce the image. These kernels are essentially very fancy edge-stopping blur kernels that reduce samples both spatially and temporally. They're guided by a large number of guide buffers that the path tracer produces. So the expectation is that most of these guide buffers are noise-free or low noise, so that the kernels can make appropriate decisions about the size of the blur kernels, how to weigh the different samples over the kernels. So what happens if this guide data is not clean, if it's noisy instead? So and that can be a challenge when there is, when the guide data just becomes noisy and the signal itself is actually quite low frequency and should be able to be denoised. So some examples where this happens is that when you have very dense geometry, so that's actually the case in the landscape scene, that you have this extremely high depth complexity and very, very fine subpixel geometry, even though the color in the end is mostly greenish yellow and should be fairly okay to denoise and blur at least some components of that. Similar with the hair rendering, that's also a case of very fine geometry. Volumes is slightly different in that a volume doesn't have a well-defined surface. It's actually defined by the random walk through it. So when you do take attributes to use for the guide data there, those are noisy by definition, and it causes problems with the denoiser. Another case that I don't have an image for is particle effects, which can also be tricky. So I will now show you the example of the landscape scene animated. So when I play this, you can see that there is a little bit of flickering left in some parts, especially in the tall grass, where there is just a lot of very thin subpixel geometry. Overall, we're still very, very happy with this result, to be able to even path trace it in real time at all, but I think there's room to tweak the denoiser a bit more. So we're coming up to the foliage here in the back, and then the camera's going to turn around and look over the pond. So you can especially see this slight flickering on the grass field here. Similar case, this is the PBRT hair scene with 6.8 million curve segments. We also used 10 bounces for this. I apologize for the rough camera motion here, but it's just really to prove I'll show you an example of where denoising is currently failing. So another interesting problem is co-design of the sampling and denoising algorithms. We already do this to some extent because we make sure to output specific guide data that the denoiser needs, and those two have been developed together. But it's often the case that the denoiser actually knows where the signal is sufficient and where it isn't. So we'd like to feed this information back from the denoiser to the path tracer to control the sampling. And path tracing, unlike rasterization, actually allows very fine-grained control over where and when to sample. So you can decide things like samples per pixel, the path length. You can even do things like dynamic path regularization to make materials on secondary bounces more diffuse dynamically to make the light transport easier. So there's just a lot of knobs that you could control to control the sampling quality, both spatially and along the paths. And the goal is really end-to-end to optimize for the best image quality. And one example we did a couple of years ago is this neural denoiser that is trained end-to-end, including the path tracing, that is then an adaptive path tracer, and then with a learning-based denoising pass. So that's an example of this kind of co-design. And once we have this kind of control, that the path tracer can be controlled at a very fine grain of where and when to sample, then the question arises, is it time for fully frameless rendering? So by frameless rendering, I mean that the denoiser and the image generation pipeline runs entirely decoupled from the sample generation. So you can imagine running the denoiser at a fixed frame rate of 60 FPS or even 120 FPS. And then for every time it needs to generate an image, it takes the currently available samples and generate the image. And then in that scenario, the path tracer will run asynchronously to add, remove, update samples, as many as it can during its continuously while it's running. The main benefit of this kind of system would be that there's no risk of dropping a frame. You always get an image out. It's just the quality of that image maybe varies. But for real time, that's a good trade-off because you do care about fixed frame rate. Also, if you get a faster GPU, then you automatically get more samples and a better image. So it has a very nice scaling behavior. With fully frameless rendering, it would be very important to think carefully about where to place your samples. And the best way to do that is through a good, for example, a blue noise sample distribution. So we had this work last year that produces this kind of spatiotemporally optimized blue noise pattern. So that's a reference for that if you're interested in frameless rendering. So now we're coming to the last of the open problems. So assume for a second that we have solved sampling and denoising, and that we can take any existing 3D content and path trace it in real time. Would we be done yet if we reach that point? And well, the answer is no, because I would say that there exists very little 3D content today that can truly produce lifelike photorealistic renderings. The world is just incredibly detailed, and this is not a problem. I'm very glad it is, but it's a fun challenge to go after. So detail exists at all scales. These are photographs taken by Benedict. So as you can see here, there's when you go closer to this branch, there's amazing detail that you see everywhere. Artists today are very good at modeling large scale detail like trees and hills and roads, but the smaller you get, the richer the detail gets, and the more tedious and time consuming it gets to model it. And it's just the sheer diversity of detail that makes it incredibly hard to do this by hand. Every object looks different close up. So just for fun, to see where we're at, I took the PBRT landscape scene, which has 4.3 billion instance triangles. And there's no critique on the modeling here. It's an amazing scene in the distance. But when you do move close to the detail in it, you realize just how much is left out. So here I'm showing some leaves, comparing those to a photograph I took when I was out running the other day. You can see that it looks nothing like the real world. So conclusion is that 4.3 billion triangles is not even close to being able to produce photorealistic results when you get close. And in a real-time scenario where the user has free control over the camera, you can't guarantee that they won't go close to a tree and actually look at the leaves. And I can only speculate that we maybe need 1,000 times more geometric detail. Here's another example. Now it's a bit unfair because I didn't find the same type of tree, but you get the point. Left is the rendering of a tree in the landscape scene. The right is a close-up of the bark on one of these trees, of the trunk. So there's really sub-millimeter scale detail everywhere. But this is not just a problem of geometric detail. Material fidelity also needs orders of magnitude improvements compared to current real-time PBR material models. This is an area where we can get a lot of inspiration from film rendering, because they, in many cases, work with deeply layered material models, and we really want to bring that kind of complexity to real-time materials. So that's a bit about the challenges of getting detail. So now let's consider for a second how real-time path tracing can help content creation. So an immediate effect is that with live feedback, whenever you make a scene edit and directly see the path trace result at 30 FPS or 60 FPS, then when you don't have to wait for the rendering anymore, then the artist's iteration loop can go faster. I think that's a very practical and near-term result that can make our content creation smoother and artists happier. But it's not going to give us orders of magnitude more fidelity. It just doesn't scale that way. So the other ways to get really detailed information is to get it from the real world through photogrammetry or other ways of extracting information. The other thing, which I think we're going to see so much more work being done is really advanced generative models for creating 3D content and creating materials, where in that case you have an AI artist creating it and then a human artist controlling it and adapting it to what you need for the particular application. So as an example of the former, photogrammetry, we've done work in our team to improve photogrammetry. So for that purpose, we built a differentiable rendering pipeline. And then with this, we can jointly optimize both the shape, so the mesh, the material properties, and the lighting. So we can get, just based on multi-view photographs, we get all of these three components out, and then we can insert the reconstructed objects in 3D scenes and edit them using traditional tools. So this is an example of just one of the test data sets. Another question that arises is, when you have this insane amount of detail that we need to represent, how is that actually going to be stored? Triangle meshes and texture maps are good at many things, but they just don't scale, even with extremely high compression, which, for example, Nanite has done an absolutely impressive job of enabling. Even with that, we're still far off, and also many things are not well represented as triangular surfaces. So I think that interesting direction is to use neural encodings for this kind of data. Through numerous examples, we've seen that neural techniques can very, very compactly be able to represent very complex data. So there's, for example, neural BRDFs. We can encode a large set of measured BRDFs with tiny neural networks, as in this paper on the right here. We've done work ourselves on nerve textures to make nerves more useful for content creation, to be able to actually texture an object with nerves. And there's work from this year about compression of neural fields, such as radiance fields, that can provide a level of detail compression of these to a very high rate. So I think this is, we're going to see so much more work in this particular field. Finally, I think no one can fail to be impressed by the advancements of the latest huge generative models, such as DALL-E 2 and ImageGen, and also StyleGAN. So all of these tools, they, however, currently produce kind of postcards. They produce 2D images of amazing things. You can tell it, I want an image of this, and you get some image that is, just extremely impressive. But imagine a future where these models are not trained to generate images, but actually trained on 3D meshes or material definitions. And you can tell it, I want a mesh that looks like this, and you get the 3D mesh out. Something like that would really revolutionize content creation. And I think it's just a matter of time. So with that, I leave you with those thoughts. That was a bit more speculative. So let's wrap up. So the first message today is that real-time path tracing is here for real-time rendering research. The PBRT scenes are no longer reserved for offline rendering research, but you can actually just go grab our source code, download the scenes, and help us solve these problems. Second message is that offline rendering and real-time rendering are now quite similar fields in that they share the same underlying algorithms like importance sampling, denoising, and so on. But there's also a bunch of different both challenges and opportunities. One is that in real time we absolutely need to make a frame every at a fixed rate every frame. So there's room for optimizing the sampling and denoising jointly, things like frameless rendering. It's also the case that content is not always perfect. Sometimes it's even user created, and the path tracer just needs to work, whatever content you throw at it. And if there's problems, then it needs to degrade gracefully. So you still get some kind of image out, but maybe it's too blurry or otherwise, but it is still a useful image at the right rate. So that's an exciting challenge. And then finally, as I talked about, getting to this dream we had of photorealistic rendering of anything. The big challenge there is really to address this, getting the detail in, both geometric and material detail, orders of magnitude more detail. So sometimes when I present real-time path tracing, I get the question that now when we can path trace in real time, is rendering now solved? And I see it from the other side, that now when we've opened this box, we can look at these assets in real time with path tracing, we'd realize just how much is left to solve. So it's a very exciting time for real-time graphics research, and that there's so many interesting problems, so many new opportunities. So big thank you for listening. I also want to call out all my collaborators across NVIDIA and academia, and of course especially the real-time rendering research team, where many of my colleagues are working. On the right here, I've included a list of references to all the papers I've mentioned in this keynote. So feel free to go look up those if you need more information. And previously, I showed the links to the Falcor research path tracer and the Slang shader compiler. So now I'm happy to take a few questions. I hope we have time for that. And thank you again for listening.
Thank you, Petrik. That was a wonderful talk. I'm surprised how far real-time path tracing has come. We are now able to take for 5 minutes a few questions from Petrik. Let's start with the one on the question board, and then others, I think you can use the come to mic option to ask questions with audio, or use the post question button to ask them in text. So the question on the question board right now is, you mentioned better caching highly improves path tracing. And according to the unofficial specs of the RTX 40XX, the caches will be far bigger. Can you say something about that already?
I can say it's true that caching helps a lot for improving path tracing. I mean, when we started going to larger scenes like the Opera House scene, one of the effects we saw that's really one of the scenes that is super limited by memory bandwidth. So 80% or so was traversal bandwidth for that, at least until we started doing more advanced shading in it. So that's a case that is super limited by memory bandwidth. And of course, if you make the caches larger, then that's going to help tremendously on that kind of scene. But of course I can't comment on pre-release specs and so on, of course.
Okay, we have another question on the question board. Can you elaborate a little bit about the BVH updates for foliage in the Tiger example? It seems like the sheer detail would end up requiring more than 2 BVH levels, and if not, that would require inordinate CPU time.
Right, that's a very good question, and it's true that there's a hard decision to make of what to put in the 2 levels of the BVH. In the Tiger scene example, we put entire trees as bottom level exposition structures. So entire trees are then instanced. You can imagine different choice, and I think the PBRT landscape scene makes a very different choice in that the individual bottom level structures are much smaller, individual leaves or individual branches. So that's really an interesting optimization problem of what to put in the top level and bottom level, and both optimize for traversal performance and also optimize for the update cost. So for the Tiger scene itself, where we put entire trees and instances and update those, the update cost was on the range of 2 to 3 milliseconds per frame, which I think was reasonable in that kind of complexity. But of course, if you have, and to be fair, I mean, the trees are largely identical trees, but they're rotated differently, and the human observer is not very, I mean, it's really hard to see that they actually a lot of copies of the same tree. So that's one trick you can use.
Got it. I also have a couple of philosophical questions while we're waiting for maybe a couple more questions from the audience. You talked about neural representation sort of also intersecting with the path that you're on. I was trying to lately we've been seeing a lot of work where NeRF-like representations have managed to produce highly photorealistic renderings of both captured and synthetic scenes. Do you think is there a path to converge with that kind of representation and rendering method?
Yeah, absolutely. I mean, I think one of the big challenges is getting this, as I talked about, orders of magnitude in more detail. And one way of doing that is to have kind of a base geometry as your triangle mesh or whatever position, and then a thin layer, a thin shell of detail on it. And that shell might very well be a NeRF-like representation that you then, when you hit it with the ray, that you then do the computation for it. So I think some kind of hybrid representation like that might very well be, one way to get to this kind of very, very detailed geometry we talked about. One challenge in NeRFs in general is that they're excellent representing captured data and reproducing that in a very, very compact way. But we also need it to be artistically controllable and animatable, and be able to interact with it in the engine. So I think that's an important open problem in some aspects of that. How to compose a scene out of NeRFs or NeRF patches in a very seamless manner and be able to animate it.
Okay. Are there any questions on the mic or on the question board? If not, I'll ask one more because this is super interesting. In your experience, what are some of were there any natural or organic changes in the artistic flow that you experienced that was specifically evolved from having a path trace or real-time path tracing application where artists chose to take or not take specified sort of more conventional behaviors because the rendering pipeline is so different?
That's another good question. I mean, we have some in-house artists that have helped us with the content here, and one feedback is that it's a relief to be able to model something and see it accurately rendered, even in real-time feedback, without having to worry about how does it differ in the, how large are the approximations than the rendered version. The approximations here, I mean, the image you get out is not, of course, truly unbiased because it's denoised, but the denoiser is fairly well understood, and we try to minimize the amount of extra blur it gives. So you get a very, very good representation of the true lighting, the true glass, and everything else you have in the scene. So that kind of feedback at least made it much easier for the artist to quickly get the right look. And that's also what we hear from other partners when we talk about them, that being able to have a reference rendering that is really quick is something super valuable in all kind of real-time applications, really.
Got it. All right, we're closing into 10:30, so let's thank Petrik again for a wonderful keynote. We will have a 5-minute break after this point, and then we will return for the diversity. Thanks again, Petrik.
Back, everybody, to HPG. And thank you very much for attending these talks. Now we are going to start with our first diversity and inclusion talk, invited talk. I'm very glad to invite Professor Cristina Nader Vasconcelos. She's now from Google Research Group. She's from the BRAIN team in Montreal, Canada. She obtained her PhD at PUC Rio in Brazil, and she worked for a long time in computer graphics, computer vision, machine learning, parallel processing. And she's now going to join us with her wonderful talk, which is sharing experiences on being a woman in computer science. Thank you very much, Cristina, for being with us here and for accepting the talk.
Thank you, Esteban. I have to say that the opinions expressed here are my own and do not express the views of my employer. And to be very honest, it's the very first time that I'm public talking about this topic. I'm much more comfortable talking about graphics, GPU programming, vision, machine learning, or even nerve models, if you wish, but not about the circumstances that led me here. But things could have gone in a different direction if I had decided to quit my path in computer science to do something else. So I decided to accept the invitation, and I thank the organizers for having me. And I hope sharing my experience can help others in finding their passions and sharing. Are we good? Okay. So moving on. Last week, I was watching the news as everybody else, and I saw the British Prime Minister saying goodbye to his job. And he said he was giving up the best job in the world. In a fraction of a second, my mind just said, I cannot agree with that. Mine is the best. I love the fact that it constantly challenged me, and the fact that I'm always learning something new. It allows me to exercise my creativity. And as I work with open problems, one day is never equal to the other. Being the hands-on person that I am, I love the full exercise of building what is initially just an idea. But it's not every day that I feel that I'm welcome or that I identify myself in the portrait of a research science or a software engineer. There are days when you go to a conference to present your work, but you are asked if you are accompanying your husband or identified as a seller person. But those are supposed to be your peers. Or when you see female models being hired for such events, aiming to attract new clients, decision makers, and talent employees, and you realize that it was not even considered that you could also be in one of those groups. Those microaggressions are hard to call out without sounding like a spoiled child complaining about small things, or sound like you're reducing the importance of the individual efforts of your peers and their merit in reaching their amazing accomplishments. But the fact is that when microaggressions accumulate, it makes it
Tell me
really
when
hard.
you do that.
Can you hear me? It makes it really hard to someone from...
Cristina,
okay.
It seems that we cannot see your slides. Can you stop and share it again?
Of course. Of course.
How's that, Nick? Not yet?
The sharing button has just disappeared.
We can't see your slides, only the video. Let's see.
Yeah, the sharing button is not on my screen anymore.
the sharing button is not on the screen anymore. So just a second. There's a lot of people trying to fix this problem.
No problem.
Just a second.
Okay, it's back here. Now I see it.
It's back again. So try to share it again.
Can you see it?
Perfect. Okay,
good.
There it goes. Thank you. I'm sorry for interrupting you.
No problem. Let's move on. So I was talking that where does this stereotype behind those microaggressions came from? I think that's the question that it's interesting that we focus on. So the modern stereotype for a software engineer or scientist is of a white boy that teaches himself how to program at a very young age, and from that age builds his professional skills, leading to a brilliant career in hit movies and series. This is the figure represented in the person of a good computer scientist. My childhood was nothing like that. My family didn't have a computer until I was a teenager, and I only had access to internet a few years later. By the way, my kids really love his story. They look at me if I were an alien or maybe from some prehistoric age. No, this was the most common scene growing up in a middle-class family in Brazil in 80s or 90s. And I have no doubt I can consider myself privileged among Brazilians and many other Latin Americans. As a young kid, I loved to build and observe things. And at school, I had a passion for math, geography, and arts. But my dream career was to become a 2D cartoon animation, as I was fascinated by the fact that animations are able to build not only new characters, but a complete new world, their own physics, their logic, rules, and an unlimited space for creativity. Later, I understood that the same thing is true for computer science, but that the impact of our creations can be extended to the real world. So I decided to apply to an undergrad course in this area without no much knowledge about it. But going back to the modern programming stereotype, I should say it was not always like that. I hope this audience already know this, but it's always good to remember that almost 200 years ago, the first programmer was, in fact, a woman, Lady Ada Lovelace. We also have to thank the development of the first compiler to a woman, Chris Hopper. When Hopper recommended the development of a new programming language that uses English words, she was told very quickly, don't do this because computers don't understand English. But she pursued it, and now we see computers that translate our programs into machine code. Up to this day, some people believe there is a social biology reason for the reduced number of women in computer science, as if women were less suited to coding than men, because of some biology better gifted men with qualities necessary to excel at programming. But if biology were the reason so few women are coding, it would be impossible to explain why women were so prominent in the early days, when the world could be far harder than today programming. Can you imagine yourself programming the devices that these two ladies used? It was a new field with a lot of math involved, and no helpful internet forums, no Google to query for assistance on your bug, or GitHub with nice instructive examples. Lady Ada Lovelace and Grace Hopper are not isolated cases, and women continue to contribute to the area up to this day. But data shows that before the 80s, the programmer workforce was much more balanced. During the 70s in the US, the number of men and women who expressed an interest in coding as a career were equal. In 1984, the percentage of bachelors in computer science graduates rose to 37%, but have declined since then to the current 18% only. Studies have shown that one of those reasons to this decline has to do with a change that happened around this date in how and when kids learned to program. Before then, pretty much every student who showed up at college had never touched a computer or even been in the room with one. Computers were rare and expensive, as we all know. Nearly all students were on equal footing and new to programming. The advance of personal computers in the late 70s and 80s remade the pool of students who pursued computer science degrees. Once the first generation of personal computers found their way into homes, teenagers were able to play around with them, slowly learning the major concepts of programming in their spare time. By the mid-80s, some college freshmen were showing up in their very first class already proficient as programmers. They were remarkably well prepared for computer science 101, for instance. As it turned out, most of them were young white men. I read about this study in a New York Times article very recently, and it was revealing to understand how this resonates with my own experience as an undergraduate student during the turn of the century back home in Rio de Janeiro, Brazil, and later as a lecturer. During my very first week as student at the university, at the Computer Science 101 Introduction to Programming class, I remember as if it was yesterday. The professor asked the students to put their hands on if they had previous experience in programming. I asked yourselves, can you guess the gender of those hands? Can you guess their skin color? If you were able to build a class simulating the distribution of world population, would you be able to point to the nationality of those hands? Back to my experience, we were 7 women among 60 students, and none of us had such a previous experience. From that very first day, the professor decided it would be better to skip trivial introductory content. And from that day on, the minority was left by themselves. It was not a surprise to me when my closest friend decided to move to another career before the end of the semester, and so did many of the other people that were left behind. Somehow, I decided to stay, keep following my curiosity about graphics, computer vision works, and machine learning. Many years later, in my own lectures, I would introduce the school year doing the same question. Do you have a previous experience in programming? But I would share my own experience and welcome newbies to programming to make their natural questions and follow their own path to discovery without looking sideways. No matter their previous experience, I would tell them that I was committed to supporting their individual growth. I'm not alone in these efforts, and I am a huge admirer of initiatives out there helping young girls and women not to only build scientific skills, but most important, creating a space of belonging in these communities. They are not limited to these slides, but I encourage students to look for those initiatives. And to fathers, maybe thinking about their daughters or members of this audience that would like to contribute to a more diverse environment to also enroll in one of those. In the last 2 years, I had the opportunity to volunteer as a mentor in the Canadian initiative focused in artificial intelligence, the AI for Good Lab. And it has my great pleasure to meet smart young women that are out there thinking about the open challenges of our society and how can artificial intelligence be used as a tool for good in facing those challenges. Computers are really an amazing and empowering tool for helping humanity in our still open major challenges, human rights, climate change, and many others. And we need people dedicated to solve those challenges, involved in the process of building the systems that will help us face it. At the same time, the ubiquitous use of systems in our main social organization creates a set of new challenges in itself. And again, here we need people that are committed to question ethics, social responsibility, and overall implications and limitations of the systems we are producing. I strongly believe we need people with diverse backgrounds and interests to be able to get deeply involved in the design, understanding, building, and decision-making process involved in the creation of those systems. My message today is simple, and it's a message of awareness. My goal today is very similar to the one I pursued while lecturing. By sharing non-stereotypical careers, I believe we can create a more welcome environment to people with different backgrounds. And the reason for doing so is not about making them a favor, no. It's because we need them. We need different voices at the decision table, and we need them to be highly skilled given the complexity of the open challenges out there. It's time for including them in the computer science picture. Thanks for listening. Sorry, Esteban, cannot hear you.
Thank you very much, Cristina. Can you hear me now?
Yes.
Very nice talk, very inspiring talk. Thank you very much for all your insights. Let's see if we have any questions here. But anyway, we are a little bit a rush of time, but I think we have time for one or two questions if someone wants to ask something. There are people saying, great talk, Cristina, very good on the YouTube here. I will just make a very fast question, and perhaps what would you say to a young Cristina that will be starting her career all after these years? I mean, what advice should we tell her?
Yes, thanks. It's a very good question. I would say just keep swimming. Just keep going, and you'll find your path.
Okay, all right. Thank you very much, Cristina. Again, thank everybody for attending the talks. And we hope to see you. We have very nice talks in the other days, and we hope have your participation over here. Thank you very much. And we will be following up with the paper presentations now. Thank you.
Okay, hello everyone. So I see the slides are still on. Maybe we can switch to, okay. Welcome to the sampling and filtering session. So the first session of HPG. We'll have 3 papers in a row. Of course, you'll be able to ask, we'll have 5 minute questions between the paper's presentation. So the first paper of the session will be Temporally Stable Real-Time Joint Neural Denoising and Supersampling. The authors are Manu Matthew Thomas from UC Santa Cruz, Gabor Lichter from Intel, Kartik Vaidyanathan from Intel, Sunggi Kim from Intel, Christoph Peters from Intel, and Angus Forbes from UC Santa Cruz. Manu will be giving the talk and will be here after to answer questions.
Hello, my name is Manu Matthew Thomas, and I will be presenting our paper titled Temporally Stable Real-Time Joint Neural Denoising and Supersampling. This is a work from Intel Graphics Research with Gabor Lichter, Christoph Peters, Sungye Kim, Karthik Vaidnathan, and Angus Forbes. The goal of our work is to improve image quality and performance of ray tracing in games. This is achieved by introducing a novel neural technique that combines supersampling and denoising. In the teaser shown here, on the left, we have a low-resolution composited input signal that is undersampled to meet real-time budget, producing noise and aliasing artifacts. On the right, we show the results from our joint approach, producing a high-resolution output image that is denoised and supersampled. Ray tracing is now widely used in games to create realistic light effects such as soft shadows, glossy reflections, and diffuse global illumination. We are still limited to a few rays per pixel for achieving real-time performance, resulting in noisy images. To reconstruct a noise-free image, we rely on spatiotemporal filters such as the analytical Unreal Engine denoiser or the statistical-based spatiotemporal variance-guided filters. Even with limited use of ray tracing effects, rendering and denoising at display resolution is expensive. Instead, we can render and denoise at a lower resolution and make use of advanced upsampling techniques to get performance gains. Recently, neural supersampling techniques such as Intel XeSS and NVIDIA DLSS are gaining huge popularity and have been successfully integrated into many games due to its ability to produce high-quality results compared to the traditional techniques. Neural denoisers produce high-quality results compared to handcrafted filters, but are not used in games due to the higher cost associated with these networks. They have become standard reconstruction techniques for offline and interactive rendering, and it's still an active area of research improving quality and performance. Designing a neural denoiser for games can be challenging because we want both real-time performance and good reconstruction quality. If we use neural denoiser at the native resolution, we would get a high reconstruction quality, but with high computational cost. We could use a neural upscaler with the neural denoiser. This would reduce the shading cost, and we would get a high reconstruction quality, but chaining two neural reconstruction techniques can be very expensive and not practical in most scenarios. Our approach is to combine denoising and supersampling into a single network that produces temporally stable, high-quality reconstruction in real time. Our network takes low-resolution input, which is noisy and aliased, and reconstructs it to a high-resolution denoised supersampled output. The first step in designing our neural denoiser is to look at the available image reconstruction networks. Chaitanya et al. Introduced the recurrent U-Net-based direct prediction network for interactive denoising. The advantage of U-Net is that it can achieve large receptive field with low cost. The downside of direct prediction is that it tends to produce ringing and color shift artifacts. Paco et al. Proposed kernel prediction networks, where the output of the network is a per pixel kernel, which is then applied to the noisy signals. Kernel predictors overcome the problem of direct prediction networks, but predicting and applying a single large kernel increases the complexity and not real-time friendly. Asselgren et al. And our previous work on quantized supersampling network explored combining U-Net with kernel prediction. Here we predict hierarchical kernels that achieve large spatial footprint with lower cost compared to predicting a single large kernel. This network is a good candidate for real-time inference. We use this network as our base design. Our U-Net feature extractor produces a shareable feature representation that is then used by the kernel predictor to generate filter weights for multiple reconstruction tasks. The shareable representation avoids the need of running separate units for each reconstruction. The noisy signal is decomposed into its different components so that the kernel predictor can generate filters designed for different noise characteristics. We have specular and diffuse, which are noisy, and we demodulate albedo from the diffuse to support aggressive filtering without blurring the texture details. The albedo is noise-free but has aliasing artifacts. We also use normal and roughness as auxiliary buffers to guide the network. Additionally, we use previous warped result to help with temporal accumulation. Providing all these buffers as input to the feature extractor directly can be expensive, since the first two convolution layers in the encoder and the last two convolution in the decoder stage must operate in the native resolution. Instead, we add a lightweight input and output block to extract features from native resolution and use the unit feature extractor in a subnative resolution, reducing the number of per pixel multiply accumulate operations. For filtering diffuse and specular, we predict hierarchical filters resembling the shape of a unit, but there are no learnable parameters associated with the filter paths. The input to the specular filter path is the noisy signal and the warped previous result. The output is the denoised specular. Diffuse filtering is similar to specular except we predict a different set of filter weights. For alias signals, a large receptive field is not required, so we only predict filter weights for native resolution. The input is the albedo containing jagged edges and warped previous result. The output is the supersampled albedo with smoother edges. The supersampled normal is only used as a guide for the feature extractor. Once we get the results from the filtering paths, we can do a composite to get denoised and supersampled result at the native resolution. We use a simple compositor where the supersampled albedo is modulated with the denoised diffuse, and then added to the denoised specular. The final component is the upsample block. Here we reuse the features from the feature extractor to predict kernels to filter at target resolution. The input is the denoised supersampled composite, and the output is the upsampled result. Here are some examples to demonstrate the effectiveness of our upsample block. We show composited results before and after the upsample block along with the corresponding reference images. Our upsampling results show sharper details on texture and fine geometry that are comparable to the reference in the target resolution. Here is the complete network architecture with a single feature extractor and multiple filtering paths. To further reduce the cost of running this network, we quantize all the non-filtering blocks to indate precision without any significant loss in image quality. To perform training, we generate all the dataset using a modified version of Unreal Engine 4. We captured several sequences with different camera paths from 6 cinematic scenes, and each sequence is labeled as train or test. The reference images are captured using 256 jitters per pixel. For shadows, we use 16 to 32 rays per pixel per jitter per light, and for reflections and diffuse GI, we use 64 to 128 rays per pixel per jitter. The network is trained in full precision mode initially, then it is retrained as a fine-tuning step with the quantized weights and activation. We use per channel symmetric quantizer for weights and per layer affine quantizer for activations. The choice of the loss function is very important to get good results. We found L1 loss to produce significant blur and loss of details with undersampled inputs. Perceptual loss functions used in image super resolution networks tend to produce sharper results. The features from VGG classification networks, which is trained on natural images, are used to define the perceptual loss. When used with our network, we observed pattern artifacts in high noisy regions. To overcome this issue, we trained a loss network on publicly available rendered images and used the features of this network to define our loss function. Our custom feature loss reduces the pattern artifacts significantly. Okay, now let's look at some results. Comparison to state-of-the-art denoisers at the target resolution reveals that our method, although receives 4 times fewer samples, is able to reconstruct image features more faithfully and achieve good sharpness. The PSNR metric is shown on top row and SSIM shown in the bottom row. When we compare with denoisers running at native resolution, we consistently see better reconstruction with our technique, while also producing a higher resolution output. To compare with neural upsampling techniques, we apply XESS to Unreal Engine 4 denoiser results. XESS brings a lot of image details compared to traditional TAA techniques, but our network outperforms at reconstructing high-frequency details as shown in the top row. Here is the video comparing all techniques to demonstrate the reconstruction quality in an animated sequence. Compared to other denoisers, our method produces temporally stable results without significant flickering or ghosting. In this close-up, we see disocclusion, and our method recovers immediately while the competing denoisers struggle to reconstruct. The character's hand moves across the scene covering the plant. As the hand moves away, the plant is disoccluded and there is not enough information to recover. UE4 denoiser plus TAA fails to reconstruct, leaving residual noise. Our network learns to predict spatial filter weights that blurs this region, providing better reconstruction when the history samples are unavailable. Like other denoisers, our technique also struggles with reconstructing specular highlights that are undersampled. In this example, we see our network reconstruct most of the scene details, but fails in the specular regions. Another limitation of our method is the reconstruction of initial frames. Since we rely on temporal accumulation, we see some noise in first few frames, but recovers quickly as we start accumulating samples. After about 5 frames, we start to see good reconstructed results. To compare performance, we use an RTX 3070 to measure timing for all the techniques. For SVGF and UE4 denoiser, the input and target resolution is 1440p, while our network takes 720p input and produces a 1440p output. For the spaceship scene, we see that our technique has better timing than Unreal Engine 4 denoiser, but slightly expensive than SVGF. The real benefit of our technique can be seen when we add the shading cost. Since we use lower resolution input, our shading cost is also significantly lower. This trend can be seen in other scenes as well. The overall cost of rendering a frame is significantly reduced without compromising the image quality. To conclude, real-time neural denoisers for games are within our reach. We show our joint denoising and supersampling solution, where one feature extractor is shared for multiple filtering tasks. Our method can provide high reconstruction quality at a lower cost. Thank you.
Thanks for the presentation, Nader. Very impressive work. We already have 2 questions on the question boards, but 3 now. Don't hesitate to actually put yourself in the question list. So I will start with the first 2 questions, which are kind of related, and they are regarding the loss you use. So you add an extra term to the loss to actually improve the quality And for that, you use kind of a custom, your custom VGG, your feature loss kind of. And the first question was, why not use a GAM for that part? Because it could also improve sharpness. And the other question by Vasconcelos is, how is it different from VGG/LPPS loss, which are both trained on like internet datasets?
Right. So yeah, so we have tried some experiments initially with GANs, but the trainings were not very stable. So yeah, we still want to pursue GAN, and it's still a future work for us. One challenge that we have is that we have several filter paths, and for each filter path we use a separate loss function. So adding a GAN would increase the training time as well. And for the second question, yes, so yeah, our feature loss is similar to VGG, but VGG is trained on natural images to for classification problems, and there are several works that shows that VGGs are sensitive to textures. So even if you don't show the object and you just show the texture, it can differentiate. So there's a texture bias, and we kind of avoid that by training with a rendered data set, and the objective of our loss function network is semantic segmentation.
I see. I was curious also because it really adds something. And were you planning to release this particular feature extractor?
No current plans to release.
No current plans. Thank you. So there's another question from Angel. Can you describe your GPU implementation and any optimization there?
Right. So yeah, for GPU implementation, we used TensorRT for all the network components. And TensorRT does a lot of optimization inside, but it's not complete yet. We could go even further with custom implementation, like fusing layers together, and we can improve the performance. And for all the non-neural network part, like the filterings are done in Vulkan.
Okay. So I had a question actually about the architecture you proposed, where you have this kind of like a big block of feature extractor that feeds into the denoising kernels, and then later you have the upsampling block. And there's actually a skip connection from that feature extractor to the upsampling block, right? And I was wondering how much impact does it have to, let's say, if you removed it, have you tried to remove it and to test whether it has an impact or not on the reconstruction?
You mean the connection from the feature extractor?
Yes. Yeah, so the output of the filtering of the denoiser is forwarded to the upsampler, but you have a connection to the features that you extracted that are also fed to the denoiser, right? For the upsampler block. And I was wondering, because you would, I mean, it surely adds something, and I was wondering how much it adds to have this skip connection.
Yeah, sure. So the final upsampling filters are predicted using these features coming from the output block, and so yeah, it is very much needed for getting the sharpness.
Okay. Okay. Well, thank you, Manu. I think we can all thanks you for this very good speak. Oh, we have a last question. Okay, have you tried training?
No, not yet.
Okay.
Right.
Thanks again. So we'll move to the next presentation now, which is Spatiotemporal Variance-Guided filtering for motion blur. So the authors are Max Oberberger and Matthaus Schasdaz from AMD, and Rüdiger Westermann from TU Munich.
Hi everyone, the title of this presentation is Spatiotemporal Variance-Guided Filtering for Motion Blur. And before we get into some technical details, maybe let's start with the last part, the motion blur, and see why we're actually interested in it. Motion blur is a pretty natural occurring phenomenon. Whenever something moves really fast in a video or photograph, it kind of gets blurry. And we can use this as an artistic effect to convey the sense of speed, for example with this Formula 1 car here. For videos it has an added benefit that it kind of blends together multiple frames and creates an optical flow between them, which is more pleasing to the eye. And for interactive media like games, we would be interested in both. We want to convey the sense of speed, but we also want a pleasant experience for the viewer. Which brings us neatly into how we can actually synthesize motion blur in computer graphics. Typically, this would be done by a post-process filter. So you'd render your scene as usual, and then you just apply a filter that blurs everything. And this is a well-researched field, and there are many different implementations which run very fast and can create some good-looking results. But they're all kind of limited by the same factor, that is that they rely on a rasterized image as an input. So what it means is there might be regions which are required for blurring that are hidden behind a different object. So whenever an object is moving behind a different object, there is detail missing. And this sort of leads to these artifacts. And this is what we typically also refer to as disocclusion. One way to solve this is to use distributed ray tracing to calculate the motion blur. This is just a brute force Monte Carlo application of ray tracing and can create some high quality and very realistic results that are on par with what you get out of an actual camera. The problem is it's quite slow. You need a lot of samples for this to converge. So naturally the question would be, is there a way to get motion blur that is fast, ideally fast enough for interactive media like games, but also creates high quality results? And if you think about it, ray tracing is actually a good starting point for this. We said it naturally solves the disocclusion problem, and to get around the high number of samples required, we can just use less samples and have some sort of denoising filter which reconstructs the final image. And this is what we've done here. We adopted the spatiotemporal variance-guided filtering that was originally introduced for global illumination to reconstruct stochastic primary rays. We take one sample per pixel and create a noise-free image from them. In this presentation, I'll walk you through the steps we took to adapt a reconstruction algorithm for global illumination to motion blur, and well, how we actually leveraged the inherent properties of it. So let's start with that first part, the spatial filter. Well, if we zoom into this image here, you can see that the samples are kind of everywhere and it's very noisy. So clearly we need some sort of spatial filter to clean this up. So the filter would scan a sort of neighboring area and evaluate samples. So what do we actually know from each individual samples? Well, if we take a look at one here, we know its position, we know its color value, but we also know its motion vector, so we know where it's going. And we can also get the timing information, so we know at which point in the frame shutter we captured this sample. And if we put all this on a pixel grid, well, using this timing information, we can know how far along the motion vector the sample has traveled. And from that we can retrace the steps and say this is where the sample has come from and this is the end position. So we get this imaginary motion line of the sample. And clearly every pixel that would be beneath this line should be influenced by this sample. Well, that's something that's really difficult to implement in parallel on a GPU. So instead of like writing our sample as information to multiple pixels, let's take a look at how we can combine information from multiple pixels into our current sample. So let's say we have this blue, we are evaluating this blue sample up here. We also have its motion vector and timing information, so we can calculate the same imaginary motion line. And if this motion line would touch a current sample, well, then the blue pixel should contribute its information to us. But we sort of want this decision to be non-binary because intersecting pixels with this line is a bit difficult. What does count as an intersection, what does not? So instead, we just calculate the shortest distance to this line. And the shortest distance indicated by the black line here, well, that's always at right angles to the blue motion line. So if you think about it, this would be the same for every sample that would use this blue motion line. So our weight function we just constructed here would sort of be like a distance field that has been cut off at either end. And that's what we use to evaluate the contribution of the blue pixel onto the red sample. Now, the question that remains is, where do we actually look for these blue pixels or the contributing samples? Scanning the whole image obviously is not a viable option, but scanning an area too little could result in subpar reconstruction. But to answer this question, let's zoom out again for a second and take a look at the entire image. Because if you consider the entire image, there are areas which need different amounts of filtering. For example, there's the background. Well, clearly no filtering is needed here. There is nothing moving here. Then there are, for example, the legs of this drone. They don't really move that fast, so there's little filtering effort needed here. But then there's also the propellers, which spin quite fast. So we'd want to do more filtering up here or scan a larger area for contributing samples. And the way we can do this is via variance-guided filtering. So we want to determine the variance in our input signal and use it to guide our filter. And the original implementation did this by calculating the variance over multiple frames. So you just compare the color values from previous frames and calculate the variance that way. For motion blur, this is a bit difficult because, well, everything's moving, and reprojecting this noisy mess we have here is kind of difficult. So we need some sort of alternative. But we can actually leverage some properties of motion blur or stochastic motion blur, because this noise is caused by things moving. So we can just look at the motion vector, and wherever there is movement, there is noise. So what we can do is just scan a local area and see and compute the motion vector, the mean motion vector length. And if the length is non-zero, well, we'd expect there to be noise. That's exactly what we found. Is if we compute the mean length, well, it's 0 for everything that isn't moving. It has a lower value for parts that are moving slow, and has a higher value for the rotating blades. So exactly what we wanted. And we can use this information to create a search window in which we look for contributing samples. And we use the motion vector length to determine the length of this search window, but we can also compute the mean direction of this motion vector and rotate this entire search window to better align with the samples we're looking for. And we can also get the variance we find in these directions. For example, if you're on a curve, well, the motion vectors aren't going to align with each other. So there's some variance in this mean direction, and we can use it to broaden the search window so that we find some samples that are in this curve segment. So now we know how we can weigh the samples and where to look for them. But there's also this temporal part which is still missing. If we go back to our input, we can see that there's a lot of areas where there's actually no sample of a moving object. So that would indicate there is some detail missing that isn't actually contained in this input. This would be detail that we couldn't reconstruct, which is, well, bad for quality. So what we want to do is we want to leverage information accumulated over multiple frames to basically fill in these gaps. What this requires us to do is to reproject a frame from our history buffer, so basically the last frame, onto a current frame. And for motion blur, I alluded to before that this is a bit difficult. So let's first look at how this would normally be done for a non-stochastic input. Typically, you have your current sample here. You would take your motion vector that brings you back to where this pixel would be in the last frame. You take a look at your history buffer, and then you do some sort of consistency checks, for example, compare the normal vectors to ensure that what you found in your history buffer is actually what you've been looking for. For motion blur, this is a bit difficult because the sample and last frame may not even be from the same object and still be valid in this case. So geometric or in general typical consistency tests don't really work. One thing we could check is if we back projected our current sample to the previous frame, well, then the previous frame should forward project to our initial position. And if that's the case, well, we found a valid sample. The problem is, what if that isn't the case? And what we came up with is an iterative search algorithm to refine the position of this blue sample here in our history buffer to one that matches with our red initial pixel. The way we do this is, instead of saying that blue should forward project perfectly onto red, we say that it should meet at the halfway point. So we take half the motion vector of each, and obviously they still not match up. But what we can do is we calculate the error between these two and use this error vector here to refine the guess or the position of the blue sample. And now we can take the half motion vector again, compare them, and if there's still some error, we can do this as many times as we want until we're satisfied with the results. So how does this look in practice? Well, here is one reprojection step. So basically we just say we go back in time and we forward project, and if they match up, they are valid. And if they're not valid, we'll color them in pink. So as you can see, most of the frame is pink here. But if we do just one of these iterations that I just explained, well, we can reproject a far greater area, basically the entire frame. And now that we have all of these samples from a history buffer, we can just add them into our spatial filter so they get combined into our final output. So now that you've seen all of the individual components, let's look how we can put them together. So we start with a ray traced input, and we calculate the variance estimate from it. And we put the color values through a pre-filter that sort of cleans up an initial bit of the noise. Then comes the first spatial filter, which is obviously guided by the variance estimate. And one thing we do here is we split the moving parts of the image from the non-moving parts, because if we blur everything that's moving, we don't want to blur any of the static geometry in the background as well, not to retain every detail we can. So we split them into two different textures and filter them individually. Then we reproject our history buffer and add all these samples from the last frame. And I alluded to before, we have the search window, but if the motion vector is quite large, the search window when we look for samples can be quite large too. So we scan the search window in a hierarchical manner. So there's still some work to do on our moving samples. And we apply 3 more iterations of a spatial filter with increasing filter kernel size onto the moving pixels and for everything that's not moving. So the static background, well, there is nothing to filter there. So that's already done. And once you applied those 3 iterations, we get the 2 final textures, and we just combine them back together for the final result. And this is what it looks like in a bit bigger. But to better show what our filter actually outputs, let's look at it in an image sequence. So we prepared this small video where we show the output of a filter, but we also compare it to the input and the reference. The key thing to look out for here is, well, we said that it should blend together multiple frames, so there shouldn't be any variance between frames. And that's exactly what you can see here. And we also compare it to a small implementation of post-process filtering. But here we compare it directly to a distributed ray tracing reference, and there is basically no, they are indistinguishable from each other. And we also compare the disocclusion problem we alluded to before, and we saw that we get better results than a post-process filter. Now here at the spinning blades of the drone, you can see there's still a bit of noise left in the blades because they're moving so fast that, well, there just isn't enough information for us to perfectly reconstruct them. But hopefully you could see that it still is a very pleasing result to the eye, and as far as we're concerned, it looks a lot better than what the post-process filter generates. But we also took a more scientific approach to evaluating a filter. And we again compare it to a distributed ray tracing output with 4096 samples. And we used the difference evaluator flip to compute an error metric. And what we found is that for basically every test scenario, we have a few areas where there are slight errors, but for the most part, we pretty much match the reference output. But there are some areas where there could be improvement. For example, our filter tends to overblur certain areas, as you can see with the fine details here on the table, as compared to the reference output. And we also can't really reconstruct fine texture details. For example, you can see there are sort of these double lines here in the reference output, which aren't really present in our output. But still, pretty much match the output pretty closely if you consider that this was the original input. So hopefully you could see that we're able to generate some high quality results, but the other condition was that we want to do this fast. So let's take a look at the performance next. And we did all these tests at 1080p, and we found that our filter runtimes were consistently below 4 milliseconds, which we would consider pretty much acceptable for real-time graphics. And even if you add the ray tracing times into the mix, we're still well below the 60 millisecond frame times would be required for 60 FPS. So to summarize what you've seen today, we showed that our filter can reduce the variance in a very noisy input and create a temporally stable output. And we can also do so at real-time frame rates. So hopefully you enjoyed this presentation, and we're happy to answer all of your questions now.
Thanks for the presentation. So yes, I remind you, you can post your question on the board or step to the mic if you want to ask a question. While we wait for a question, I have a couple actually.
Sure.
It looks to me, I'm curious, what kind of actually random sequence per pixel do you use to generate your path traced renderings?
You mean for the time values, right?
Yes, exactly.
Okay. What is it called? We tried a couple of them, but they're all pseudo-random. Nothing like real pseudo-random number generators. Nothing that does some. I tried to remember the name. We have it. I think we have it in our paper.
Okay. So did you try to use the blue noise detected sampling, for example, that could help distribute the error so that it will be even okay? Because
we did nothing to the path trace or the ray tracing input. We just used random values for the time and just saw the output of the ray tracing stack as the given, the not to be touched, and just used the output from that to do our filtering.
Okay. In my experience, adding this little step just helps a lot the denoiser. So maybe you could have even greater results. And actually, for the filtering stage, so you basically take the kind of the average motion, the filtered motion, and you try to align the filter with respect to this motion. And I was curious as if, for example, you have an extreme motion. Basically, you only want to filter along a 1D line. You don't want to filter outside of this line.
You sort of have to get enough samples in. So this is why when I showed you a weight function, we sort of added this bit of leeway to either side with the distance, because if you just do the intersection, so only you take exactly what's on this line of movement, that's not enough. You don't get good results from that. That's also probably where this, as I just said, the overblurring, you sort of get that, but in motion you don't really notice it. But if you sort of just take the line, there's still some flickering, for example. It doesn't get temporally stable.
Because you have to,
and you would notice that more You don't really
because
notice.
you have too many chances of hitting something there's there's nothing at all. Okay, I had another questions about like so all your tests were done at 1 sample per pixel, if I'm correct. So there you have the explicit notion of what's in motion and what's not in motion, because you only have 1 sample. So 1 pixel represents exactly 1 sample. But if you had 4 samples per pixel, like how would you do that?
We thought about it, and we would probably need them either pre-separated. So if you accumulate them before, you would have to have 2 results, like all the samples that have moved, all the samples that haven't moved, or just give all samples directly. Like, do not accumulate them at all. Just have, for example, 4 buffers with 1 sample each.
Okay, I see.
Because we cannot distinguish. If we split the moving from the static, we cannot distinguish if they're all pre-meshed up.
Exactly. Okay, so I don't see any question there. I actually had another one. I mean, it's like more like kind of an broader area question. In the paper, you mentioned that like for shadows, basically, since you don't have motions, it's very hard for you to be able to filter along that time. Do you have ideas of direction where you could go to solve this issue?
You would also probably need the shadow rays or the information from the shadow rays as a separate input. Because if you just do secondary rays or whatever and just have the shadow baked into your color value, well, there is no way to separate them again for the filtering, because if something moving from shaded to in light, well, the shadow doesn't move with the object. But in our case, it would. So you would just blur that shadow. You wouldn't have like a hard line. So you'd need to have the shadow as like a separate input. But it also gets difficult because, well, you need some reconstruction filter for the shadow again. We thought about it, and it sort of gets complicated combining this with any secondary ray effect. Like reflection is the same thing. If a glossy sphere moves, the reflection stays perfectly sharp. So it's difficult to integrate this with secondary rays. You would have to probably do what we did, decrease the variance in like the primary rays, and then do the secondary rays separately.
I see. Well, thank you again for your presentation. Now I think we can move to the last talk of the session. And this talk will be entitled Virtual Blue Noise Lighting. The authors are Tianhui Li, Wenyu Wang, Daiki Lin, and Chemyut Sel from the University of Utah. And Tianyu and Wenyu will be giving the talk.
Hello everyone, I'm Tianyu from University of Utah. I'm glad to be here to share our paper, Virtual Blue Noise Lighting, with you. My co-author Wenyu is another first author of this paper. Here is a group of images comparing our method to prior virtual light methods using VPL, VSL, and rich VSL. As you can see, our method can render the clearest glossy reflection on the box behind Buddhas. We achieve this by improving virtual light placement, distribution, and sampling and emission profile computation. Before introducing our method, let's recap the prior work on virtual light methods. Rendering with virtual lights, also known as instant radiosity, is a two-pass algorithm. In the first pass, we trace random light passes and place virtual lights at each vertex along these light passes. The second pass is final gathering. Indirect illumination is handled by computing direct illumination from all virtual lights. Conventional VPL cannot properly handle specular transport. We can solve this problem by using virtual spherical lights. VSL distributes the energy over nearby surfaces inside an imaginary sphere. This removes the singularity of the geometry term, but it also leaves a cone integral to solve, which can be costly. Using VSL does not produce splotches like VPL with specular transport, but the results of VSL can be blurry. Rich VPL is a more recent technique to improve specular transport using waterlights. For rendering more challenging situations like this scene, Rich VPL uses waterlights with emission profiles and compute emission profiles from a photo map. However, after adding direction emission profiles, a waterlight becomes very expensive, thereby limiting the number of waterlights that can be used in practice. Considering this limitation, the waterlight placement becomes much more important. In our paper, we introduced various improvements to the rendering pipeline with waterlights. As a result, our method provides a better illumination estimation and faster convergence during rendering. We identify three main problems in prior waterlight methods. Problem 1 is wasted waterlights. These are waterlights that have no contribution to the final image. For example, in the rich door scene you see here, there are very few waterlights inside the room. This results in a poor illumination estimation, forming splotches you see in the rendered image on the left. If we step outside, you will see where all other waterlights are. They are placed outside of the room and do not contribute to the final image. So this is an extreme example. It's not uncommon to have a large percentage of waterlights with no contribution to the final image. Problem 2 is hot zones, where a significant portion of light passes go through are often oversampled with many waterlights, even when their contribution to the final image could be effectively approximated using fewer waterlights. In this example, a large portion of waterlights are placed close to the original light source. Other areas are not sampled adequately. In our method, we address problem 1 and problem 2 by generating waterlights starting from the camera. As you can see, this results in a much better sampling of the room. Problem 3 is that random sampling leads to many waterlight pairs that are placed too close to each other, which is another source of waste. Also, there are large gaps between waterlights, resulting in a poor distribution of waterlights. We address this problem by generating a blue noise distribution of waterlights. This significantly improves the quality, particularly for glossy and specular surfaces. We address problem 1 and 2 by generating waterlights starting from the camera. This ensures we do not waste space with unused waterlights, and we do not place too many waterlights around hot zones. We address problem 3 using sample elimination to get a blue noise distribution of waterlights. Note that some of these problems were recognized in prior work as well, but the solutions we describe are much more effective. Please see the paper for a more detailed discussion of prior work. Here is an overview of our virtual blue noise lighting, VBNL method. It begins with generating initial candidates from camera. Then it performs parallel adaptive sample elimination for blue noise distribution. The next step is computing the emission profiles by tracing photons. Finally, we sample the waterlights during rendering. I'm going to explain these 4 steps in this order. We begin with waterlight generation from camera. To address problem 1 and problem 2, we generate waterlights from the camera. We start by tracing a camera ray to find the primary heat position X, and then we can extend the path to get the position of a waterlight position candidate Y. This guarantees that all the waterlights we generate contribute to the final image. In addition, the local density of waterlights is proportional to camera importance. This addresses problem 2, the hot zone problem. The waterlights we generate this way form a random distribution. Yet, these are not the final waterlights. They are all the initial candidate positions. Next, we improve the distribution of our watchlets to achieve a blue noise distribution using sample elimination. Let's say the difference between a random distribution and a blue noise distribution. Our target is to achieve a blue noise distribution with our watchlets to address problem 3. We achieve this via sample elimination. First, we generate more watchlets than we need. Then, we apply sample elimination to strategically remove some of them and achieve a blue noise distribution. So, with sample elimination, we eliminate some candidates. Then, we can get watchlets with blue noise distribution. This is an example showing the distribution of initial candidates. Variance, right? And after sample elimination, it's difficult to find any two watchlets are still grouped together. However, using the same Poisson radiance disk is not always good. If you check the reflection of the bottles on the table, you will find that the reflection disappears. In that sense, uniform sample elimination can be worse than random sampling. So for rendering glossy reflection using watchlets, we might want to keep the origin sample density, because the origin density contains information about camera importance. We address this problem by using adaptive sample elimination. We adjust the Poisson disk radius of each watchlet based on the initial density. With adaptive sample elimination, we can preserve the density of initial candidates. This preserves the glossy reflection in this example. In the paper, we also describe a method for performing sample elimination in parallel. Our parallel sample elimination splits the sampling domain into subdomains with equal samples. We use a balanced KD tree to partition sampling space. We begin sample elimination in the leaf nodes of the tree. Then, we merge them and continue sample elimination. For this scene, eliminating more than 1 million samples, parallel sample elimination is almost 10 times faster in a 12-core CPU. We have talked about how to get a blue noise distribution of watchlets. So far, the watchlets are just placeholders. They do not have any emission information. Now, it's time to compute their emission profiles using photon splitting. This step starts with photon tracing. Instead of storing a photon map, we generate each photon and find the watchlets around the hit point, and distribute its energy to the nearby watchlets. We call this process photon splitting. After that, we do not need to store the photon. This way, we can efficiently use a large number of photons for estimating the incoming radiance for each watchlet. We use a alhedral map to store direction incidence radiance information. After photon tracing, we have all incident radiance stored in such a alhedral map. Then, we use a compute path to radiance conversion to convert the incident radiance to algo radiance. Algo radiance is stored in an alhedral map as well. Here is an example incident radiance map. Let's convert it to an algo radiance map, which is the emission profile. This is a video clip showing that how emission profiles change during photon tracing. All our emission profiles are packed into a single texture called mega texture. After computing the incident radiance, we convert all incident radiance map to algo radiance map, representing the emission profile of our watchlets. So we finished computing emission profile for watchlets. Now, let's talk about watchlet sampling. After computing emission profiles, we have our watchlets with direction emission information. Next problem, how can we sample them efficiently? Let's try power-based sampling first. It's not surprising to say that power-based sampling cannot give us a good result. Then, let's try live-BBH sampling, which is a hierarchical sampling technique. Even with this, we cannot get much improvement. Can we do better? The answer is yes. This is a result of BSDF sampling. So how can we achieve this? For BSDF sampling, requiring nearby ultralights to decide the final light samples. When we pay its short distance ray tracing, which is very fast. This way, we get rid of explicit cone sampling for spherical lights. Also, instead of one light sample, we can use one BSDF ray to sample all ultralights that overlap with the hit point. Compared with the light BVH and power-based sampling, BIDF sampling spends less time and the convergence is much better. We can even do better with multiple impedance sampling. Compared to BSDF sampling alone, we can get better results and only slightly increase the cost. Instead of MIS, we can also try to combine our sampling technique with raster. We can even get better results, but because of the overhead, we pay more computation time for raster sampling. If we use the same shading time, our MIS can generate better results. Now, we have our sampling strategy, but we can still encounter other problems. Especially, we may have undersampling problem. With highly specular material, we can clearly see these artifacts. That's because when we hit a highly specular surface, the specular lobe is narrow, so for this estimated area, we do not have enough ultralights. Undersampling also happens near corners, as can be seen in this image. This is because if the shading point is too close to the corner, even with a large lobe, the ultralight density can still be insufficient. To avoid undersampling, we introduce adaptive camera passage theorem. First, we estimate the footprint of the sampling lobe, use the distance between the shading point x and the hit point y, PBSDF, which is the PDF of the BSDF impedance sampling, and the geometry term. Then, we can estimate number of ultralights inside this estimated area by multiplying it with the ultralight density. Fortunately, we already compute the ultralight density per light for adaptive sampling elimination during our ultralight distribution process. Based on this N, the estimated ultralight count will make a decision. If N is large enough, we use the ultralights that overlap with the hit point Y. If N is too small, we conclude that we do not have sufficient ultralight density, so we extend the camera path similar to path tracing. In addition, to avoid visible sharp changes from one sampling method to another, we use two parameters N minimum and N maximum. If the estimated count is lower than N minimum, we always extend the path. If it's larger than N maximum, we always terminate the path. Between N minimum and N maximum, we do both and blend the results. This is the result without passage theorem. You can see, with passage theorem, most artifacts due to undersampling disappears. This image shows the average path length. As you can see, these are more bounces near corners because this path need more ultralights to shade. We have finished introducing all the components of our method. Let's see some results. The first is the kitchen scene. Let's compare our method to rich VSL, using images rendered with the same number of ultralights. Rich VSL take longer shading time than our preparation plus shading time. In addition, rich VSL also requires a much longer ultralight preparation time. Still, our method produces clearly superior results. Compared to path tracing with MIS and light BVH, using the same shading time, our method can produce closer results to the reference. And if we give path tracing our entire computation time, our result still has lower noise. When it comes to a more challenging scene, the rich door scene. Again, rich VSL takes much longer preparation time and shading time, but our result still has much less noise in this scene. It's not surprising, path tracing does not work well in this scene. Even with the same total time, our result has much less noise. The quality improvements or rich VSL can be attributed to the improvement of our ultralight distribution. Compared with rich VSL, our method automatically places VSLs with a higher density where prominent specular reflections appear. In rich dosing, because rich VSL generate waterlets on photon's position, only a few waterlets are placed inside the room. Our waterlets are generated from cameras, so we don't have the undersampling problem of other waterlet methods. In conclusion, we have introduced the virtual blue noise lighting that improves the indirect illumination estimation pipeline using waterlets. Unlike typical waterlet generation that relies on light passes, our method uses camera passes for waterlet placement. Then, we combine this approach with an adaptive sample elimination strategy that leads to a blue noise distribution with varying density. Furthermore, we describe a photon splitting method that can efficiently use a large number of photon passes for generating the emission profiles of waterlets. We combine BSDF sampling and power-based sampling with MIS to improve the illumination estimation from our waterlets during shading. Moreover, we have described an adaptive camera pass extension technique for resolving undersampling. You can find more details in our paper and supplemental document. Our project page includes a link to the source code of our implementation using a GPU ray tracer in Falcon. Thank you for listening.
Thanks for the presentation, Janu. So again, people, you can either step to the mic, or if you're shy, yes, we have Daiki, which
can you hear me?
Hello, can you hear me?
Okay, yes, you can ask your question now. Yes.
Here is a demo of our render.
Oh, okay. So actually, I had a question, which two things weren't very clear to me during the presentation. So maybe we can start with the first question in the question board. In the adaptive sampling elimination, can you weight samples to reduce their chance of elimination for the specular cases?
Good. Do you mean the sample elimination stage can improve the performance of sampling specular effects?
Is it okay? Can you hear me, Janu?
Yeah, I can hear you.
Yeah, okay. So regarding the questions, is it fine to?
Sorry, do you want me to ask it verbally?
Yes, if you can.
Sorry, I was just watching. Obviously, I haven't seen the paper, but just watching the process, it seemed like you were subdividing the screen down and basically reducing the number of samples as you went down till it got down to you got to reasonably even density. But if you instead weighted your samples, can you reduce it down so it's not so much so that the sums of I don't know how you would put it. I guess you'd have to have a reciprocal for the more important thing, but so the sums of each region came to be about the same. That way, if you have this case where you need more samples for something which is very concentrated, the specular stuff, it would automatically compensate.
Actually, what we do is adaptive sample elimination. So you can imagine in path space if they are high frequency paths. So basically, during our initial candidate generation, we will put more samples for where high frequency specular effects happen. So, and then we will compute adaptive Poisson disk radius. So, which can ensure us remain more samples for these places.
Okay. Oh, that's probably equivalent then. Okay, thank you.
Okay, so I have another question, which is basically when in the sampling density you showed, where we can see the samples after sample elimination, it seems that because you're doing a first bounce on the geometry to know where the light position will be, you will have some kind of acoustic of any specular material you will have, and so you have a higher density in region that do not necessarily have high density for the lighting. I was wondering whether this is something that would help for performance-wise to solve or not, and if it is something that you've tried to compensate.
Yeah, that's a good question. Yeah, only considering BSDF sampling during initial sample generation can be not enough. So we have in our future work we want to try like gradient information and guided initial candidate generation that can be more robust. Yeah.
So I want to add something. So actually, this strategy of tracing rays from camera to put VPLs actually works well for most things we tested. And maybe the issue you just mentioned, like caustics, actually, if the caustics is not really high frequency, then usually the camera VPLs generated from camera will still have a well enough placement for capturing those caustic effects. So unless you have very high frequency caustics, which probably need the higher density of VPLs there. So for rendering those, maybe we want to kind of blend a strategy of also generating some VPLs from the light.
Okay, so my point was well that because you're sampling from the camera, you can have acoustic, but from the importance of the camera. Yeah. And this will not reflect the density of like, it will be oversampling a region in space, but really doesn't need that much samples, contrary to the rough or the specular samples you need to add to better convey the acoustics.
Yes, but actually we've tested a lot of things, and we found that this camera generation, VPL generated from camera, actually provides very robust rendering quality in all sorts of scenarios. Yeah.
Okay. Thanks. So I had the last question. Basically in the rendering step, so the last step after the virtual point lights generation, you do BSDF sampling. Do you any specific sampling strategy, like I don't know, maybe a specific sequence for random number generation or something that improves the quality, or is just pure random? And I guess
we just use pure random for this BSDF sampling. Yeah, I haven't tried other things.
Okay. Well, thanks for listening, and I think we can all thank the speaker for this session, and move to the next one.
Have you ever wanted to see realistic ray trace caustics in real time, but you have no recent powerful GPU with hardware ray tracing support? Don't worry, here's an alternative way to render the ray trace caustics using only an image space technique. We introduced bidirectional image space ray tracing, which basically traces a ray from a light first using reflective shadow maps, and then traces another ray from a camera using a G-buffer, just like we typically do in screen space reflection and refraction. And finally, we merge those trace paths using a denoiser. Take a look at the comparison between caustics mapping and our approach. You can see that our caustics have sharper edges and smoother intensity gradient. At the same time, we also achieve the caustics outside the light view that doesn't exist in caustics mapping result. Let us show you how our solution makes high-quality caustics affordable for everyone in the poster session. Thank you and see you there!
Eye-based point rendering is a new algorithm that combines the geometric parallelism of view-independent rendering with new eye resolution shading efficiencies throughout the pipeline to make real-time multi-view effects more practical. Standard multi-view rendering renders a scene 6 times per cube map, often requiring dozens of geometry traversals per frame and repetitive computation of lighting within each eye pixel. We demonstrate eye-based point rendering by applying it to dynamic cube map reflections. In a scene with millions of triangles and 20 reflective objects, eye-based point rendering generates 10 times fewer points than view-independent rendering and is over 3 times faster than multi-view rendering with comparable visual quality. Furthermore, our algorithm enables drastic speedups of recursive reflection without any additional pipeline paths or buffers. Visit us at the poster session to find out more. Thank you.
Imagination presents its new triangle bisection tessellation with fractional LODs as a superior alternative to existing methods. It uses per vertex tessellation factors rather than per edge. A patch is initially subdivided into one subtriangle per edge. Bisection is applied to all subtriangles when a tessellation factor exceeds a threshold. The new vertex inherits its own tessellation factor. The algorithm supports quad, triangle, isoline, or any polygonal domain. Vertices have fixed UV coordinates, ensuring stable geometry as tessellation factors change. Blending is used to provide fractional LOD support. A child vertex is assigned a displacement factor. Displacement factors are derived from tessellation factors of parent vertices. The displacement of a child vertex is given by interpolating between its full displacement and the average of its parent vertices. Blending can be performed for any attribute, not just displacement. Here is the modified pipeline with an optional hull shader and new fixed function blender. Thank you for listening.
Hello everyone, this is Chewy from Zhejiang University. I'm glad to present the solution of ray tracing denoise combined with super resolution. It uses only the RGB noise image and motion vector. It needs the geometry information like normal or depth, which reduces the bandwidth of rendering output. Also, the combined super resolution ability reduces the dominant computation as 1/4, which is estimated to about 40 gigaflops. We also analyze the blending and skip weights from the intermediate layers to verify our design methodology. One interesting side product is that the analyze indicating that the segmentation backbone networks may benefit the ray tracing denoise task. Thank you.
We propose an adaptive extension of the Dynamic Diffuse Global Illumination or DDGI technique. DDGI is a probe-based GI technique that places probe on a regular grid and populates them with uniform sampling. With a fixed sample budget per frame, increasing the probe count reduces the number of samples per probe. As such, the technique fails to capture transient dynamic changes in a scene due to a less than desired concentration of resources per probe. Our adaptive extension aims at improving resource concentration in critical areas. We define several heuristics identifying the important probes, such as probe close to the camera and geometric surfaces, and probes recording a change in visibility and irradiance. We quantify the heuristics by tracing pilot rays and use multiple parallel Markov chains to sample the important probes. Our approach reduces lag and improves transient response to dynamic changes in the scene. Come to our poster to learn more.
We present opacity map compression for ray tracing. Modern APIs perform ray triangle intersection, but run a shader to do alpha tests. introducing latency. This can soon add up and be costly. But many tests are a clear hit or miss. We'd prefer these to be done early in ray triangle hardware. At HPG 2020, Gruen et al. Presented opacity masks. The mask has 3 states per region: fully opaque, fully transparent, or run the shader. Maps are accessed from barycentrics. No texture mapping is required. We propose using a square map per triangle pair. See poster for reasoning. Higher resolutions give better savings, but bigger maps use more storage and bandwidth. We use VQ compression. It's simple to decode and allows random access. With 2x2 vectors, we found uniform cases are common. We avoid storing these in the codebook and dedicate 3 indices. The data often has symmetries. We have 3 per quadrant transformations to reduce the number of unique vectors. Thank you for listening.
Hi, I am Dhaval. I am going to present learn transfer for surface geometries. Pre-computed radix transfer is widely used method to obtain ray tracing effects for low frequency eliminations in real-time applications. It achieves it by disentangling the rendering equation into transfer and lighting and pre-computing them individually. Most previous methods relied on mesh-based geometries, either storing transfer at vertex space or UV-mapped texture spaces, both inherently requiring a tabulated structure in the geometry. The main drawback of previous methods is it is not very easy to address geometries with no inherent tabulation, like SDFs. Hence, we propose to use transfer regressing neural networks trained in a supervised fashion, which takes sample data as input and regress the transfer values as output. We club the regress transfer at runtime with rule product formulation to obtain the diffuse and glossy renders. The geometry used here is SDF along with the network evaluation per fragment while obtaining real-time frame rates. Please check out our process during the poster session.
Okay, so that was the end of the fast forward. So we are going to end the broadcast now. So for those of you who are following us on Twitch and YouTube, the video should be taken down soon. So we hope to see you tomorrow. And normally for those of you who are following us on OEA, you've all been moved to the poster hall, hopefully.